Look up at the night sky on a clear, dark evening, away from the city's glow. If you're lucky and you know just where to look, you might spot a faint, fuzzy patch of light that seems almost like a smudge on the cosmos. It doesn't twinkle like a star, it just hangs there, a soft and unresolved glow. What you're seeing is not a single star or even a distant galaxy. You are witnessing one of the universe's most ancient and enigmatic structures, a globular cluster. Imagine, if you can, a city of stars, not a sparse neighborhood like our own solar system, but a metropolis so densely packed that if you were standing on a planet within it, your night sky would blaze with the light of tens of thousands of stars, each as bright as Venus appears to us. These are the ancient celestial cities floating in the vast, silent halo of our galaxy, and they hold secrets that have baffled astronomers for centuries. They are relics from the infancy of the cosmos, and they are far stranger than they appear. For a long time, we thought we understood them. We saw them as simple, predictable balls of old stars, beautiful but ultimately quiet retirement homes for stellar generations that formed long ago. But now, with powerful new telescopes and sophisticated technology, we are peeling back the layers of these cosmic time capsules, and what we are finding is utterly astonishing. The quiet retirement home is in fact a hive of bizarre activity. We are discovering stars that shouldn't exist, gravitational anomalies that defy explanation, and phenomena that challenge the very laws of physics as we know them. Each new observation seems to unravel another piece of our fundamental understanding of how the universe works, suggesting that these clusters are not just simple collections of stars, but rather the key to unlocking some of the deepest mysteries of space, time, and matter itself. This video is a journey into that profound mystery. We are about to embark on an exploration of 50 of the strangest, most mind-bending discoveries ever made about globular clusters. We will venture into their densely packed cores to find intermediate mass black holes. We will uncover the mystery of their multiple populations of stars, and we will question why some of them seem to be surrounded by vast halos of dark matter. This is not just a list of facts, it is a voyage to the frontiers of human knowledge, a story written in starlight that is still being decoded. So, prepare to have your perception of the cosmos shifted, because the truth about these glittering islands in the sea of space is more incredible than anything we could have imagined. Our journey into the strange begins with a discovery so fundamental it threatens to shake the very foundations of cosmology. It is a puzzle born not from the faint, distant edges of the observable universe, but from the heart of our own galactic neighborhood. For decades, astronomers have worked to determine the age of the oldest stars, using our understanding of stellar physics as a cosmic clock. A star's lifespan is dictated by its mass. The larger and brighter it is, the faster it burns through its hydrogen fuel. The smaller, cooler stars, known as red dwarfs, can shine for trillions of years, but the massive, brilliant stars live fast and die young. When a star begins to run out of hydrogen in its core, it leaves what is called the main sequence, evolving into a red giant. By identifying the point in a cluster's population where the most massive stars are just beginning this transition, a feature known as the main sequence turnoff, scientists can calculate the entire cluster's age with remarkable precision. It is a reliable and elegant method trusted for generations. Yet, when this method was applied to some of the Milky Way's most ancient globular clusters, like M92 and NGC 6397, the results were nothing short of shocking. The calculations pointed to ages of around 14 billion years. This number, on its own, is staggering, representing almost the entire history of existence. But the problem emerges when we compare it to the age we have calculated for the universe itself. Using measurements of the cosmic microwave background radiation, the faint afterglow of the Big Bang, and by refining the expansion rate of the universe, known as the Hubble constant, cosmologists have arrived at a very precise age for the cosmos, approximately 13.8 billion years. This creates an impossible paradox. How can a star be older than the space and time in which it resides? It is like finding a fossil that predates the formation of the Earth. This age crisis presents us with a profound choice. Either our methods for dating the stars are fundamentally flawed, or our understanding of the universe's birth and expansion is incomplete. The implications of this discrepancy ripple through astronomy, forcing a re-examination of our most basic assumptions. One possibility is that our stellar evolution models need adjustment. Perhaps the chemical composition of these ancient stars is different than we think, or physics operates in subtly different ways under the extreme densities found within a globular cluster, affecting how quickly a star consumes its fuel. The other, even more radical possibility is that we have miscalculated the Hubble constant. The rate of the universe's expansion is one of the most critical numbers in all of cosmology, and if it is slightly slower than we currently believe, it would mean the universe is actually older, potentially resolving the paradox. This single, perplexing observation from these ancient star clusters has therefore become a central battleground in modern science, pitting our understanding of stellar life cycles against our model of cosmic evolution. It reminds us that sometimes the biggest mysteries are not found in the unknown voids, but in the very details of the objects we thought we understood best. If the age paradox forces us to question our cosmic timeline, then the next discovery shatters our understanding of the clusters themselves. For over half a century, the textbook description of a globular cluster was elegant in its simplicity. A vast, spherical swarm of stars, all born from the same primordial cloud of gas in a single, frantic burst of star formation. They were considered the ultimate example of a simple stellar population, a snapshot of a single moment in cosmic history, with every star sharing the same age and the same basic chemical recipe. This idea was comforting. It meant these clusters were straightforward laboratories for studying stellar evolution. But like so many comfortable ideas in astronomy, it turned out to be completely wrong. The first cracks in this pristine picture appeared not with powerful space telescopes, but through painstaking observations from the ground. Astronomers, using increasingly sensitive spectrographs to analyze the starlight from individual stars within clusters, began to notice something peculiar. They were looking for specific chemical fingerprints, particularly the abundances of elements like sodium and oxygen. In a simple stellar population, you would expect every star to show nearly identical levels of these elements. But that's not what they found. Instead, they discovered distinct groups of stars. One group had the expected chemical signature, high in oxygen and low in sodium. But another group, often a significant portion of the cluster, showed the exact opposite pattern. Their light revealed they were enriched with sodium and depleted in oxygen. This was not a minor variation. It was a fundamental chemical difference that pointed to a radically different origin. This was the revelation of multiple stellar populations, and it sent a seismic shock through the field of astrophysics. How could two groups of stars living side by side in the same dense cluster have such different chemical histories? The pristine gas cloud from which the first generation of stars formed would have contained only the elements forged in the Big Bang, primarily hydrogen and helium with trace amounts of lithium. Heavier elements, which astronomers collectively call metals, are cooked up in the nuclear furnaces of stars and scattered into space when those stars die in spectacular supernova explosions. Therefore, any star enriched with these heavier elements must have formed from gas that was already polluted by a previous generation of stars. The presence of a second generation of stars within a globular cluster means that the cluster must have held onto enough of its gas after the first stars were born to form a second batch, or it somehow accreted fresh gas from outside. Both scenarios are incredibly difficult to explain given what we know about the violent lives and deaths of massive stars. Imagine a gigantic nursery where 100,000 babies are born at the same time. Now imagine that a few million years later, a second group of babies appears in the same nursery, but these newborns have a different genetic code, one that could only come from the first group. The first generation of massive stars would have lived short, violent lives and then exploded, their supernova releasing unimaginable amounts of energy. Standard theory predicts that this ferocious stellar winds and shockwaves would have blown any remaining star-forming gas clear out of the cluster, effectively shutting down any further star formation. Yet, the evidence written in the starlight tells us that somehow, against all odds, a second generation did form. The current lead theory suggests that the polluters were not the supermassive stars that go supernova, but a specific class of intermediate mass stars that, in their late stages, shed their outer layers through strong, relatively gentle winds. These winds, rich in processed elements like sodium and aluminum but lacking in oxygen, could have polluted the cluster's central regions without completely clearing it out, providing the raw material for a new round of star birth. This process implies a far more dynamic and complex childhood for these ancient clusters than we ever dreamed, turning them from simple retirement homes into cosmic crucibles with dramatic, multi-act histories. Just when we thought we had a handle on the complex lives of these star cities, another mystery emerges, one that involves the darkest and most powerful objects in the universe. We've come to accept that supermassive black holes, weighing millions or even billions of times the mass of our Sun, lurk at the centers of most galaxies. And we know that stellar mass black holes, the remnants of exploded massive stars, are scattered throughout. But what about the middle children, the theoretical missing link between these two families, intermediate mass black holes? These would be the cosmic heavyweights ranging from a few hundred to a few 100,000 solar masses. For a long time, globular clusters seemed like the perfect place to find them. It made perfect sense. A dense, massive collection of stars would provide the ideal nursery for a black hole to form and then grow, either from a single colossal star in the early universe or through the merger of many smaller ones. Their immense gravity would naturally settle them in the very center of the cluster's core, acting as a hidden anchor for the entire stellar metropolis. Astronomers have spent decades hunting for these objects, using some of our most powerful observatories. The search hinges on detecting the subtle gravitational influence such a black hole would have on the stars swirling around it. If one is present, the stars at the very heart of the cluster should orbit at incredibly high speeds, a telltale sign of a massive, unseen object pulling them along. We see this effect spectacularly at the center of our own Milky Way, where stars are whipping around an invisible point, confirming the existence of Sagittarius, a star, our resident supermassive black hole. So, scientists pointed their telescopes toward the cores of nearby globular clusters, expecting to see the same frantic stellar dance. Yet, for the vast majority of clusters, the results have been bafflingly quiet. The stars in the center simply do not move fast enough. In cluster after cluster, the observed velocities are far lower than what the presence of an intermediate mass black hole would dictate. It's as if you calculated the weight needed to anchor a spinning carnival ride, but when you look, the central post is simply not there. The ride is spinning, but the expected anchor is missing. This absence creates a profound puzzle. If these black holes did form, as theory strongly suggests they should have, then where did they go? One compelling and dramatic possibility is that the clusters themselves have violently ejected their central black holes. The core of a globular cluster is a gravitational battlefield, a chaotic environment where stars and black holes are in a constant dance, interacting and exchanging energy. Through a process known as dynamical friction, a single, heavy object like an intermediate mass black hole would tend to sink toward the center. But if it interacts with a binary system, a pair of stellar mass black holes, for instance, the complex gravitational encounter can act like a cosmic slingshot. The interaction can transfer a tremendous amount of energy to the intermediate black hole, giving it a gravitational kick powerful enough to fling it entirely out of the cluster and into the lonely interstellar void. It's a scenario where the very density that should nurture a black hole ultimately becomes the instrument of its exile. Alternatively, perhaps these black holes never formed in the first place. Maybe the conditions within globular clusters prevented the growth of a single dominant black hole, or perhaps stellar mass black holes interact in such a way that they are ejected before they can ever merge into a larger object. This ongoing mystery forces us to reconsider not just the life cycle of black holes, but the very stability and evolution of these dense stellar environments over billions of years. But if the apparent absence of intermediate mass black holes leaves a gravitational void at the heart of these clusters, the next discovery fills that void with something even more wondrous and improbable: entire worlds. For decades, the prevailing wisdom was clear and seemingly unassailable. Globular clusters are the last place in the universe you would ever expect to find planets. The reasoning was rooted in the very thing that defines them: their extreme density. Picture our own serene galactic neighborhood, where stars are separated by light years of empty space, providing a stable, quiet cradle for planetary systems to form and endure for billions of years. Now contrast that with the core of a globular cluster, where stars are packed together 1,000 times more tightly. In such a stellar metropolis, a star's closest neighbor might be as near as our own solar system's outer planets. In this chaotic environment, gravitational encounters are not rare events. They are a constant fact of life. A star passing even remotely close to another star's planetary system would act as a gravitational bull in a cosmic china shop, its pull either flinging planets into the cold depths of interstellar space or sending them careening into their parent star. The very idea of a stable, long-lasting orbit in such a gravitational maelstrom seemed like a fantasy. This is what made the discovery in the globular cluster Messier 4 or M4 so revolutionary. Astronomers were studying a unique system, a binary pair consisting of a pulsar, the rapidly spinning, ultra-dense corpse of a massive star, and a white dwarf. In 2003, careful analysis of the pulsar's incredibly regular radio pulses revealed a tiny, repeating anomaly, a slight variation in the timing of the pulses. This could mean only one thing: a third, much smaller body was tugging ever so slightly on the pulsar, an effect known as a timing delay. The culprit was a planet with a mass roughly 2.5 times that of Jupiter, orbiting the binary system. The existence of this world, given the prosaic name PSRB 1620-26b, was a staggering contradiction. It had somehow survived, not in the sparse outskirts of the cluster, but deep within its stellar throng. This was not a planet that had drifted in from the outside. Its orbit confirmed it was a native, formed in this seemingly hostile environment. The discovery of this pulsar planet forced a complete rethink of planetary resilience. How could a world endure in a place where gravitational stability is a luxury? The answer may lie in the unique circumstances of its birth. This particular planet orbits a system that has already undergone the most violent events a star can experience: supernova explosions. It's possible the planet formed in a second act from a disk of material surrounding the neutron star after its cataclysmic birth, a scenario that would make it a true child of cosmic chaos. Its very existence proves that the processes of planet formation are not limited to the quiet nurseries of galactic disks. They can occur even in the most extreme conditions. It suggests that if planets can form and persist here, in the dense, ancient core of M4, then they could be far more common throughout the universe than we ever suspected. This opens up the breathtaking possibility that even within these glittering, ancient cities of stars, there could be countless worlds orbiting suns, places where the night sky is a permanent, brilliant spectacle of neighboring stars, a vista forever alien to anything we know. While the survival of planets in a globular cluster challenges our ideas of stability, another discovery presents a paradox of time itself, one that is written in the very color of the stars. If you were to look at a color magnitude diagram of a typical globular cluster, a kind of census that plots each star's color against its brightness, you would expect to see a very distinct and predictable pattern. The vast majority of stars fall along a clear curve called the main sequence, with hot, bright blue stars at the top and cooler, fainter red stars at the bottom. Then there is a branch where stars have evolved off the main sequence, becoming red giants. Since all the stars in a cluster were born at roughly the same time, this diagram should tell a single, coherent story of stellar aging. The most massive stars have already lived out their short lives and died, leaving behind the longer-lived, lower-mass stars. This logic dictates that no hot, bright blue stars should remain in an ancient cluster. They should have all burned out billions of years ago. Yet, when astronomers peer into these clusters, they find a population of rebels. These stars are defiantly blue, luminous, and seemingly young, lingering in a part of the diagram where they have no right to be. They are the blue stragglers, and their existence is a beautiful violation of the rules. The name blue straggler perfectly captures their nature. They are stragglers, lagging behind the rest of their generation in the race to evolve, and their blue color signifies a hotter, more vigorous state than their neighbors. It is as if you attended a reunion for a high school class that graduated 50 years ago, and among the crowd of retirees, you find a few individuals who look like they are still in their 20s, full of youthful energy. The immediate, naive question is, did these stars form recently? But that is impossible. The environment within a globular cluster has been devoid of the necessary gas to form new stars for almost the entire age of the universe. So the blue stragglers are not young stars. They are old stars that have found a way to cheat death, to reset their internal clocks and extend their prime. They are stellar vampires and cosmic crash survivors, and their secret lies in the unique social dynamics of a densely packed star cluster. Astronomers have developed two compelling theories to explain how these stars achieve their renewed youth, and both are direct consequences of the extreme density in a globular cluster. The first and perhaps most dramatic theory is stellar collision. In the calm suburbs of the galactic disk where our sun resides, stellar collisions are so astronomically rare as to be practically impossible. But in the core of a globular cluster, where stars are packed together like commuters in a rush-hour subway, close encounters are inevitable. When two lower-mass stars, perhaps similar to our Sun, collide and merge, they combine their hydrogen fuel into a single, more massive star. This new composite star is now heavier than either of its progenitors. Since mass dictates a star's lifespan, more mass means a hotter core and faster fuel consumption. This newly merged star would, paradoxically, behave like a younger star. It is suddenly brighter and hotter, appearing blue, even though the combined age of its components is ancient. It's a cosmic case of two middle-aged stars combining their resources to create a single entity that acts with the vitality of a teenager. The second theory involves a less violent but equally fascinating process: mass transfer in a binary star system. Many stars in clusters are born in pairs, gravitationally bound to one another. If these two stars are close enough and one of them begins to expand into a red giant as it ages, it can start to transfer its outer layers of hydrogen gas onto its smaller companion. The receiving star, gorging on this fresh fuel, becomes more massive. Its increased mass reignites its nuclear furnace with greater intensity, making it hotter and bluer, effectively reversing its evolutionary track. The donor star, stripped of its outer layers, is left as a faint white dwarf, while its partner shines with a stolen youth. This process transforms a sedate binary system into a glaringly bright blue straggler. In a sense, these stars are not stragglers at all, but rather the beneficiaries of cosmic cannibalism, having extended their lives by consuming their neighbors. Determining which mechanism is dominant has been a key challenge, and the clusters themselves may hold the answer. In the incredibly dense cores of clusters where stellar encounters are most frequent, the collision model seems the most likely creator of blue stragglers. We might expect to find them concentrated right in the heart of the action. In the slightly calmer outer regions, the slower, more gentle process of mass transfer in binary systems could be the primary method. By mapping the locations of blue stragglers within different clusters, astronomers are piecing together a picture of their origins. These stars are more than just cosmic curiosities. They are direct evidence of the complex interplay and dynamic relationships that define life in a crowded stellar environment. They show us that even in a society of ancient stars, there are pathways to a second act, proving that the story of a star cluster is not one of simple, passive aging, but one of continuous interaction and transformation. The resilience of blue stragglers clinging to youth within the safety of their cluster presents a story of survival, but not all stars are so fortunate. For every cluster that holds together, there is another that succumbs to a far more dramatic and destructive fate. This brings us to a discovery that shows us the ultimate end for many of these ancient structures, an end written not in the brilliant core of a cluster, but in a faint, ghostly river of stars strewn across the heavens. We have to shift our gaze from the tight-knit communities to the lonely ghosts of clusters that are no longer there. Our own Milky Way galaxy is not a gentle host. It possesses a tremendous gravitational field, and as globular clusters orbit the galactic center, they are subjected to intense tidal forces. Think of it as the difference between swimming in a calm pond and swimming near a powerful drain. The gravitational pull from the galaxy is stronger on the side of the cluster closest to the center and weaker on the far side. This difference, the tidal force, constantly tugs and stretches the cluster. Each time the cluster swings through the dense galactic plane or makes a close pass by the central bulge, it experiences a gravitational shock, a tide that pulls stars away from the cluster's outskirts, particularly those already on loosely bound orbits. For billions of years, this process acts like cosmic erosion, slowly stripping the cluster of its stars. The stunning evidence of this destruction is a phenomenon known as a stellar stream. These are not clusters, but long, thin, ribbon-like structures that arch across the sky, composed of thousands of stars all moving together in a coherent river of light. They are the skeletal remains of a star system that has been completely disrupted. The most famous and dramatic example of this is the GD1 stream. Stretching for dozens of degrees across the northern sky, GD1 is an incredibly faint trail of stars, so diffuse that it was only mapped in detail by powerful digital sky surveys like the Sloan Digital Sky Survey. What makes GD1 so significant is its purity. It is a long, coherent stream with no visible cluster at its head. This tells astronomers that the demolition project is complete. The parent globular cluster has been entirely dismantled, its stars now following the same orbital path their home cluster once did, a phantom procession marking a grave in space. By studying the exact path, length, and density of a stream like GD1, astronomers can perform a kind of cosmic archaeology. They can rewind the clock, tracing the stars back to their point of origin to learn about the cluster that once was. They can even use the stream to map the invisible gravitational field of the Milky Way itself. The subtle gaps and kinks in a stream are like fingerprints, left by close encounters with dark matter clumps or the gravitational influence of smaller satellite galaxies. These streams act as incredibly sensitive probes of the galaxy's unseen structure. The story of GD1 is a sobering one. It shows us that the majestic globular clusters we admire today are not permanent fixtures. They are temporary constellations slowly being consumed by the galaxy they orbit. Their dramatic lives, filled with stellar collisions and binary interactions, can all be erased by the relentless, large-scale gravity of the Milky Way, leaving behind only a silent, flowing testament to their former glory. While the ghostly streams of disrupted clusters show us the power of the galaxy's gravity, there is another, even more profound gravitational mystery hidden within the clusters that remain intact, a mystery concerning what is not there. This brings us to one of the most significant and puzzling distinctions in all of astronomy, a discovery that forces us to confront the nature of the universe's most elusive substance, dark matter. To understand this puzzle, we need to compare two types of objects that, on the surface, can appear remarkably similar: globular clusters and dwarf spheroidal galaxies. Both are compact, spherical collections of hundreds of thousands or even millions of stars. They can have comparable total masses and sizes, yet when we measure how they move, we find a difference that is absolutely fundamental. The key lies in a concept called the mass-to-light ratio. Astronomers can measure the total amount of light coming from a system. That is straightforward. They can also estimate the system's total mass by observing how fast the stars within it are moving. According to the laws of gravity, the speed of a star orbiting within a system is directly related to the total mass contained within its orbit. The faster the stars move, the more mass must be present to hold the system together. In our own solar system, for example, Pluto moves much more slowly around the Sun than Mercury does because the Sun's gravitational grip is much weaker at that vast distance. When scientists apply this technique to dwarf spheroidal galaxies, they find something extraordinary. The stars are moving far too quickly for the amount of visible mass we can see. The calculated mass based on stellar velocities is often 10 to 100 times greater than the mass we can account for from all the stars, gas, and dust combined. This missing mass is the signature of dark matter. It appears that these small galaxies are embedded within enormous, massive halos of this invisible material, which dominates their gravity and dictates their structure. They are essentially lumps of dark matter with a sprinkling of stars inside. Now perform the same analysis on a globular cluster. Measure the velocities of the stars whizzing around its center. The result is completely different. The observed stellar motions are exactly what you would predict based on the gravitational pull of the stars themselves. There is no discrepancy. The mass you calculate from the motion matches the mass you can see in the form of stars. In other words, globular clusters appear to contain little to no dark matter. They are, for all intents and purposes, self-gravitating systems of pure, visible stuff. This is a profound and strange dichotomy. Two objects that look similar in size and stellar population are governed by completely different rules of gravity. One is dominated by the invisible, the other by the luminous. This absence of dark matter in globular clusters is a major headache for theories of how they formed in the early universe. The leading model for the formation of large-scale structure suggests that the first things to condense out of the primordial soup were small, dense clumps of dark matter. These clumps or halos acted as gravitational seeds, pulling in ordinary gas from which the first stars and galaxies then formed. According to this picture, any large, bound structure of stars that formed early on should naturally be sitting inside one of these dark matter halos. Dwarf galaxies fit this model perfectly, but globular clusters, which are just as ancient, do not. They seem to have formed without this dark matter anchor. How is that possible? One compelling idea is that globular clusters did not form in isolation within their own private dark matter halos, but instead were born within the much larger, turbulent gas clouds that were collapsing to form the first giant galaxies. In this scenario, the incredible density of gas and the fierce pressures from intense star formation could have been enough to create these tightly bound balls of stars without the need for a significant dark matter component to hold them together. They would be products of their environment, born in a frenzy of stellar birth within the budding galaxy itself, rather than as independent islands. Alternatively, if they did initially form with their own dark matter halos, perhaps the clusters have since lost them. Billions of years of orbiting through the strong tidal field of the main galaxy could have gradually stripped away the more diffuse dark matter halo, while the densely packed star cluster, being more compact and robust, survived. This, however, is difficult to reconcile with the fact that some of the most distant, isolated globular clusters, which have experienced minimal tidal stripping, also show no signs of dark matter. The implications of this dark matter puzzle are far-reaching. It suggests that the early universe had at least two distinct pathways for building stellar structures. One pathway via dark matter halos led to dwarf galaxies. Another, perhaps triggered by the extreme conditions within giant molecular clouds, led to the creation of these pristine, dark matter-free globular clusters. Understanding why these two paths diverged is crucial for piecing together the full story of cosmic dawn. The silent, dark matter-free nature of globular clusters, therefore, is not a minor detail. It is a critical clue, a fossilized imprint from a time when the first structures were assembling, telling us that the recipe for building a star cluster is fundamentally different from the recipe for building a galaxy. If the tranquil streams of disrupted clusters represent a slow and graceful death, then the next discovery showcases the opposite extreme: stars that don't drift away gently but are catapulted into the void with unimaginable force. We are entering the realm of the hypervelocity star. Our galaxy is a gravitational prison. For a star to achieve escape velocity and break free from the Milky Way's pull requires an extraordinary event, a cosmic slingshot of unbelievable power. For a long time, the only conceivable source of such energy was the supermassive black hole at the galactic center. The theory was elegant. A binary star system wandering too close to Sagittarius, a star could be torn apart, with one star captured and the other flung away at a significant fraction of the speed of light. But then astronomers began finding these renegade stars, and to their astonishment, their trajectories did not point back to the galactic center. Instead, they seemed to originate from a completely different source: the ancient globular clusters orbiting in the galactic halo. The mechanism for creating these stellar cannonballs is one of the most dramatic demonstrations of gravitational physics at work. It begins, like so many cluster mysteries, with a dense environment where binary star systems are common. Imagine a tight binary pair, two stars locked in a mutual orbit, drifting into the chaotic core of a globular cluster. Here, they may have a close encounter with a tremendously massive object. While the hunt for intermediate mass black holes has been challenging, many clusters are known to host a central concentration of mass, a gravitational anchor that could be a single black hole or a tight knot of stellar remnants. As the binary system approaches this central massive object, a complex gravitational dance unfolds. The three bodies interact in what is known as a gravitational slingshot or Hill's mechanism. The immense gravity of the central object acts like a lever, tearing the binary pair apart. It captures one of the stars, binding it into a tight orbit, and in doing so, transfers a colossal amount of kinetic energy to the other star, which is then ejected at an incredible speed. The velocities involved are staggering. A typical hypervelocity star can be shot out of its cluster at speeds exceeding 800 kilometers per second. To put that in perspective, our own Sun orbits the galaxy at a sedate 220 kilometers per second. These stars are moving so fast that they are not just leaving their parent cluster behind. They are on a one-way trip out of the Milky Way entirely, destined for the empty vastness of intergalactic space. They become lonely travelers, each one a solitary sun on an eternal journey through the cosmic dark. The discovery of these stars was a complete surprise, turning the idea of globular clusters from quiet retirement communities into active launch sites for interstellar escapees. It provided indirect but powerful evidence for the presence of a very massive object at the hearts of some clusters, even if that object remains shrouded in mystery. The existence of hypervelocity stars opens up a fascinating new window into the dynamics of our galaxy. By tracking their paths backward across the sky, astronomers can potentially triangulate the location of the clusters that ejected them, even if those clusters are now far away. These stars act as cosmic tracers, their trajectories mapping the gravitational fields they pass through. Furthermore, studying these stars themselves is a unique opportunity. They are time capsules from the interiors of globular clusters, offering a chance to analyze the chemical composition of a cluster star without the challenging glare of its thousands of neighbors. As they race across the galaxy, they carry with them the pristine signature of their birthplace, a chemical fingerprint that can tell us about the conditions within the cluster from which they fled billions of years ago. Their incredible journey is a testament to the violent forces that can simmer beneath the serene appearance of a glittering star cluster, proving that these ancient cities are not just static relics, but dynamic engines capable of launching stars on voyages of epic proportions. If the hypervelocity stars are the dramatic escape artists of the cluster, then the chemical fingerprints we find on the stars that remain are the silent, smoking gun of a much older, more profound drama. This evidence takes us beyond the dynamics of gravity and into the very nuclear furnaces that forged the elements of the universe. For a long time, the chemical makeup of globular cluster stars was thought to be a simple affair. But as our spectroscopic tools grew sharper, they revealed a level of complexity that was completely unexpected, a chemical landscape that is bizarre, inconsistent, and points directly to a series of extraordinary events that must have occurred in the cluster's youth. The story begins with the basics of stellar nucleosynthesis, the first generation of stars in a cluster, often called population 2 stars, formed from the pristine gas left over from the Big Bang. This gas was almost entirely hydrogen and helium. Every single element heavier than helium, what astronomers call metals, had to be forged inside stars. The first massive stars to ignite in a cluster would have been true pioneers, the first factories to produce elements like carbon, oxygen, and sodium. When these short-lived giants exploded as supernova, they would have seeded the surrounding gas with their newly created elements. So, when the second generation of stars formed from this enriched gas, they should have contained a measurable amount of these metals. This much was expected. What was not expected was the specific and peculiar pattern of that enrichment. When astronomers analyzed the light from individual stars in a cluster like Omega Centauri or Messier 13, they found that the second-generation stars weren't just uniformly richer in metals. They showed a very specific and puzzling chemical signature. Certain elements were significantly enhanced while others were curiously depleted. The stars showed unusually high levels of helium, sodium, and nitrogen. At the same time, they showed marked deficits in carbon and oxygen. This is not a random pattern. It is a very specific fingerprint that points to a particular type of nuclear fusion process. The classic fusion chain that powers most stars, the CNO cycle, provides a crucial clue. In the hot cores of massive stars, hydrogen is fused into helium using carbon, nitrogen, and oxygen as nuclear catalysts. The cycle doesn't create or destroy these elements overall, but it does change their proportions, converting carbon and oxygen into nitrogen. What we see in these chemically peculiar stars is the signature of material that has been processed through this cycle. The gas they formed from was rich in nitrogen because the carbon and oxygen had been converted into it. But the CNO cycle alone doesn't explain the elevated helium or sodium. This is where the mystery deepens and the suspects in this cosmic chemical drama are narrowed down. The polluters could not have been the very first supernova, as their explosive yields would have included a much broader and different set of elements like iron and silicon. Instead, the evidence points to a different class of star altogether, intermediate mass stars, specifically those between about 4 and 8 times the mass of our Sun. These stars live a different life and die a different death. They never become supernova. Instead, in their late giant phase, they undergo a process called hot bottom burning. In this phase, the convection in their outer layers becomes so intense that it drags material from the deep, hot interior, where the CNO cycle is active, up to the surface. This processed material, now enriched with helium, sodium, and nitrogen, and depleted in carbon and oxygen, is then gently expelled into space through strong stellar winds. This is a far more controlled and specific form of pollution than a violent supernova. It's the difference between a targeted chemical spill and a full-scale industrial explosion. This scenario paints a vivid picture of the early cluster, the first generation of massive stars, including these intermediate mass polluters, would have formed quickly. Over a few million years, the polluters would have reached the end of their lives, shedding their processed outer layers in a gentle, persistent rain. This enriched gas would then mix with the remaining pristine gas in the cluster. But here lies another major puzzle. How did this gas avoid being blown completely out of the cluster by the supernova from the first generation's most massive stars? One possibility is that the cluster was massive enough to gravitationally hold onto some of this material, concentrating it in the core. Another is that the gas shed by the intermediate mass stars was denser and cooler, allowing it to fall to the center and form a second generation before the cluster's potential supernova could clear it all out. This intricate chemical drama reveals that globular clusters were not just simple star-forming regions. They were complex ecosystems with multiple overlapping phases of stellar life and death, each leaving its unique mark on the next generation. The strange abundances we see today are a permanent record of that fleeting, dynamic era, a testament to a time when these ancient cities were not quiet retirement homes but vibrant and chaotic stellar nurseries. Just when we thought the case against massive black holes in globular clusters was settled, a discovery within a cluster called M54 delivered a stunning reversal, forcing us to reconsider the entire rulebook. The story of this cluster is unique from the very start because M54 is not like the other globular clusters orbiting our Milky Way. It doesn't actually belong to us. This dense sphere of stars is the core of a small galaxy that our own galaxy is in the process of consuming, the Sagittarius dwarf elliptical galaxy. This distinction is crucial because it blurs the line between what we define as a globular cluster and what we define as the nucleus of a galaxy. And at the heart of this ambiguity, astronomers found something they never expected: a supermassive black hole. For years, the search for intermediate mass black holes in globular clusters had yielded frustratingly little evidence. The stellar motions in most clusters suggested that if a central black hole existed at all, it was relatively modest. But when a team of astronomers turned the powerful spectrographs of the Very Large Telescope in Chile toward the center of M54, they measured the velocities of stars whipping around its core and got a shock. The speeds were immense, indicating the gravitational pull of a truly colossal object. The data pointed to a black hole with a mass of around several thousand times that of our Sun. This was not the elusive intermediate mass black hole astronomers had been hoping to find. This was something far larger, an object that dwarfed any black hole ever suspected to lie within a globular cluster. It was, for all intents and purposes, a bona fide supermassive black hole, akin to the one at the center of our own galaxy, just on a slightly smaller scale. This discovery created an instant and fascinating puzzle. Was M54 the exception that proved the rule, or was it the key to understanding a whole new class of object? The leading interpretation is that the black hole was never part of the globular cluster itself. Instead, it was the central engine of the Sagittarius dwarf galaxy. In larger galaxies, it is well established that a supermassive black hole resides at the very center, a gravitational anchor that grew along with the galaxy itself. M54, being the dense, bright core of its original galaxy, likely came with this black hole as a standard feature, As the Milky Way's gravity stretched and tore the Sagittarius dwarf apart, stripping away its outer stars over billions of years, the resilient core and its massive black hole remained intact, now appearing to us as just another globular cluster in our halo. This revelation transforms M54 from a simple star cluster into a cosmic fossil of a dramatic galactic merger. It suggests that some of the other globular clusters orbiting the Milky Way, especially the brightest and most massive ones, might not be native to our galaxy at all. They could be the remnant cores of other small galaxies that were devoured long ago, each potentially hiding its own supermassive black hole. This idea, known as the galactic cannibalism model, paints a vivid picture of our galaxy's history. The majestic halo of globular clusters we see today may be less like a collection of distant suburbs and more like a trophy case displaying the conquered hearts of ancient rival galaxies. The presence of this overmassive black hole in M54, therefore, does more than just challenge a single notion. It invites us to look at every ancient cluster with a new question. Are we looking at a simple ball of stars, or are we witnessing the final, glittering remnant of a galaxy that once was? Yet this relentless process of tidal stripping, while destructive, also creates something of profound scientific value. As stars are gradually pulled from the outer regions of a cluster, they do not simply vanish into the galactic background. Instead, they follow the orbit of their parent cluster, forming vast, elongated streams that trace a path through the galactic halo. These are the tidal tails, and they are far more than just the debris of a dying cluster. They are exquisite tracers, cosmic breadcrumbs that map the gravitational landscape of the entire galaxy. The discovery of these faint, river-like structures required a new kind of astronomy. They are too dim and diffuse to be seen by the human eye, even through a powerful telescope. Their existence was only confirmed with the advent of massive, digital sky surveys that could meticulously catalog the positions, colors, and motions of millions of individual stars across the sky. By filtering out the foreground stars of the Milky Way, astronomers were able to reveal these faint, coherent flows of stars, all moving in concert like a school of fish in a dark ocean. The most stunning aspect of a tidal tail is the information it encodes. The very length and shape of the stream are a direct record of the cluster's orbital history. A long, smooth, and symmetrical tail indicates that the cluster has been orbiting peacefully for billions of years, steadily losing stars along its path. But if the stream shows kinks, gaps, or bends, that is evidence of a gravitational disturbance. These imperfections are the fingerprints of a past close encounter. The culprit could be a clump of dark matter, a dwarf galaxy that passed nearby, or even the gravitational ripple from a merger with another galaxy in the distant past. By studying these subtle irregularities, astronomers can use the tidal tail as a sensitive detector for the invisible mass structures that populate our galaxy. It's a remarkable reversal. The destruction of a star cluster gives birth to a tool that allows us to see the unseen gravitational forces that shape the cosmos. Beyond the stream itself, there are the individual stars that manage to escape the cluster's grasp entirely. These are the extra-tidal stars, loners that have been liberated from the cluster but haven't yet aligned into a clear stream. Finding these stars is like finding needles in a galactic haystack, but their discovery provides critical, real-time evidence of the stripping process. Each one is a testament to the cluster's ongoing evolution, a refugee from the dense stellar city now embarking on a solitary journey through the galaxy. By studying the chemical composition of these escapees, astronomers can gain a clean reading of the cluster's stellar makeup without the challenge of observing them amidst the bright glare of the cluster's core. They serve as pristine samples, confirming that the processes we believe are happening at the edges of these clusters are indeed actively shaping their fate. The presence of these tidal tails and extra-tidal stars completes the life cycle of a globular cluster, showing us that even in their dissipation, they continue to contribute to our understanding of the universe, painting a dynamic picture of gravitational interaction on a galactic scale. But the story of tidal tails and galactic cannibalism leads us to a specific cluster that presents a gravitational riddle all its own, a puzzle that begins with its very structure. If you were to turn a powerful telescope toward the constellation Pegasus, you would find Messier 15, or M15, one of the oldest and most densely packed globular clusters known in our galaxy. At first glance, it appears as a typical, magnificent sphere of ancient stars, but when astronomers began to meticulously map the distribution of its hundreds of thousands of suns, they uncovered something peculiar happening at its very heart. Unlike many clusters where the stellar density increases steadily toward the center, M15 exhibits what is known as a core collapse. This means the rise in density is not just a gentle slope, it is an extraordinarily steep gradient, a dramatic concentration of stars into an incredibly small, blazingly bright central region. To understand just how extreme this environment is, consider the scale. The core of M15, where this density cusp occurs, is a volume of space only a few light-years across. Within that tiny cosmic pinprick, thousands of stars are crammed together. If you were standing on a hypothetical planet near that core, your night sky would not be a dark canvas with pinpoints of light. It would be a permanent, blinding daylight from the combined glare of countless stars separated by distances comparable to those between our Sun and its nearest stellar neighbors. This level of crowding has profound consequences for the stars trapped within. Close encounters, near misses, and even direct collisions become not just possible, but inevitable over the cluster's 13-billion-year lifetime. The core becomes a gravitational pressure cooker, where stellar orbits are constantly being shuffled and altered by the relentless pull of their neighbors. This extreme central concentration naturally led to one of the most compelling hypotheses in modern astronomy, the presence of an intermediate mass black hole. The logic was straightforward and powerful. A single, massive object at the very center would act as a gravitational anchor. Its immense pull would naturally draw stars inward, creating the very kind of steep density cusp observed in M15. It would be the cosmic equivalent of a drain, pulling the surrounding stars into a tighter and tighter configuration. For many years, M15 was considered one of the best candidates in the entire sky to host such a black hole. The evidence seemed to be pointing directly to a hidden monster lurking in the core, its presence betrayed only by the frantic dance of the stars it governed. However, as observational techniques improved, the plot thickened. When astronomers trained the Hubble Space Telescope on the heart of M15, measuring the velocities of individual stars with unprecedented precision, the results were unexpectedly ambiguous. The stellar motions were indeed very fast, suggestive of a significant central mass, but the data did not conclusively point to a single, massive black hole. Instead, the observations could also be explained by a different, and in some ways even stranger, phenomenon, a dense concentration of stellar remnants. In the frenetic environment of a collapsed core, the most massive objects like neutron stars and stellar mass black holes would naturally sink to the center through a process called dynamical friction. Over billions of years, this could lead to the formation of a central, dark cluster, not a single giant black hole, but a tight knot of dozens or even hundreds of these dark, compact corpses, whose combined gravity could mimic the effect of a single intermediate mass black hole. This leaves the true nature of M15's core as one of the most hotly debated topics in stellar dynamics. Is it a single, definitive anchor or a swarm of dark objects? The answer has major implications. A central black hole would suggest a specific formation path, perhaps from a single seed object in the early universe. A dark cluster, on the other hand, would be a spectacular demonstration of the long-term effects of dynamical evolution, a natural endpoint for a very old, very dense system. Unraveling this mystery requires peeling back the layers of this stellar onion, using the subtle motions of the stars as clues to weigh the invisible mass at the center. M15, therefore, stands as a perfect laboratory for testing our theories of how dense stellar systems evolve over cosmic time, its mysterious heart challenging us to distinguish between one giant gravitational beast and a crowded graveyard of smaller ones. While the mysterious heart of a cluster like M15 presents a gravitational puzzle, another discovery within these dense stellar environments offers a tool of unparalleled precision for unraveling the fabric of spacetime itself. This discovery revolves around a specific type of stellar remnant that turns the chaos of a cluster's core into a laboratory for fundamental physics, the millisecond pulsar. To understand their significance, we first need to understand what a pulsar is. When a massive star explodes in a supernova, its core can collapse into an incredibly dense ball of neutrons, a city-sized object containing more mass than our Sun. This neutron star spins rapidly, and if it has a powerful magnetic field, it beams radiation from its magnetic poles like a cosmic lighthouse. If one of those beams sweeps across Earth, we detect a regular pulse of radiation, a tick-tock of radio waves or X-rays with a stability that rivals our most accurate atomic clocks. These are pulsars, the dead spinning hearts of once giant stars. Now, take this already remarkable object and subject it to the unique social dynamics of a globular cluster. A solitary pulsar born from an isolated supernova will gradually slow down over millions of years as its radiating beams sap its rotational energy. But in a globular cluster, a pulsar is rarely alone. It often has a companion star, and here the magic happens. Through the process of mass transfer we discussed with blue stragglers, the pulsar can act as a gravitational vampire. If the two stars are close enough, the pulsar's intense gravity can pull material from its companion. This material falling onto the pulsar doesn't just pile up, it transfers angular momentum, effectively spinning the pulsar up to incredible speeds. The result is a millisecond pulsar, an object that can rotate hundreds of times per second, its pulses becoming so regular and rapid that they function as the most precise natural timepieces in the known universe. And globular clusters are absolutely teeming with them. Despite containing less than 1% of the Milky Way stars, globular clusters are responsible for over 80% of the known millisecond pulsars in our galaxy. This incredible abundance is a direct consequence of their high stellar density. The crowded core provides countless opportunities for a neutron star to capture a companion and begin this process of cosmic spin-up. This makes each cluster a veritable forest of ultra-precise cosmic clocks, all ticking away in synchrony. But these clocks do more than just keep time, they are exquisitely sensitive detectors. Any slight deviation in their rhythm, any minuscule variation in the timing of their pulses, is a clue, a signal that something is affecting the path of their light or the flow of time itself. One of the most profound applications of these pulsars is testing Einstein's theory of general relativity. The theory predicts that massive objects warp the fabric of space-time, and that this curvature affects the path of light and the passage of time. By observing a millisecond pulsar in a binary system with another dense object, like a white dwarf or even another neutron star, astronomers can monitor the pulsar's ticks with incredible precision. They look for tiny changes in the pulse arrival times that are predicted by relativity, such as the orbital decay due to the emission of gravitational waves. The first such binary pulsar discovered, which earned its discoverers a Nobel Prize, provided indirect but stunning confirmation of gravitational waves. In the dense environment of a globular cluster, the chances of finding such rare and informative binary systems are greatly enhanced, turning these ancient star cities into ideal testing grounds for the most subtle effects of gravity. Beyond testing fundamental laws, these pulsars also act as probes for the invisible environment within the cluster itself. As the pulses from a millisecond pulsar travel across the vast distance to Earth, they pass through the thin gas that drifts between the cluster's stars, known as the intra-cluster medium. This gas, though incredibly diffuse, is not a perfect vacuum. When the radio waves pass through it, they are slightly delayed, an effect that depends on the frequency of the wave. Lower frequency radio waves are slowed down more than higher frequency ones. By measuring this delay across different frequencies, astronomers can calculate the total electron content along the line of sight, essentially weighing the amount of invisible ionized gas within the cluster. This provides a unique way to study the remnants of stellar winds and the gentle gravitational breathing of the cluster, material that is far too faint to see directly. Sometimes the timing anomalies reveal something even more dynamic. If a pulsar's signal suddenly shows a significant and complex delay, it can be a sign that the pulsar is passing behind a specific, small cloud of gas within the cluster, perhaps a shell of material ejected from a recent stellar event. In this way, the unwavering tick of the millisecond pulsar becomes a searchlight, illuminating the subtle, invisible structures that fill the space between the stars. The abundance of these natural clocks in globular clusters has therefore transformed them from mere objects of beauty into active, living laboratories. Each precise tick is a data point, allowing us to conduct experiments in gravitation and plasma physics on a cosmic scale, experiments that would be impossible to set up anywhere else in the galaxy. This journey through the destruction and dynamics of clusters within our own galaxy sets the stage for a puzzle that unfolds far beyond the Milky Way in the quiet depths of the constellation Fornax. Here we find a challenge to our understanding of how these stellar cities form, not from a single cluster, but from a startling mismatch between a galaxy and its entourage. The dwarf spheroidal galaxy in Fornax is a cosmic minnow, a small, faint, and diffuse collection of stars that is a mere satellite to the much larger Fornax cluster of galaxies. By all accounts, it should be a quiet, unassuming backwater. Yet, this diminutive galaxy possesses a treasure that seems wildly disproportionate to its size, a population of globular clusters that is not just present, but spectacularly bright and numerous. To appreciate the strangeness of this, we need to consider the standard relationship between a galaxy and its globular clusters. For large spiral galaxies like our Milky Way, the rule is fairly consistent. The more massive the galaxy, the more globular clusters it tends to have. Our galaxy, with a mass of hundreds of billions of suns, hosts about 150 known globulars. The dwarf spheroidal in Fornax, by contrast, has a total stellar mass thousands of times smaller than the Milky Way. You would expect such a tiny galaxy to have very few clusters, if any at all. Instead, it boasts at least 6, and these are not faint, insignificant specks. They are exceptionally luminous, some of them ranking among the brightest globular clusters known in the entire local group of galaxies. It's the cosmic equivalent of a small, rural village somehow supporting a skyline of 6 gleaming, world-class skyscrapers. The sheer efficiency of cluster formation in this low-mass system appears to be off the charts, defying our models of how star formation proceeds in such gentle gravitational environments. This Fornax mystery forces astronomers to confront a fundamental question: what conditions are truly necessary to birth a globular cluster? The leading theory for their formation involves immense pressure. In the early universe, we think clusters formed within giant, collapsing clouds of gas that were subjected to extreme external pressures, perhaps from cosmic shocks or the intense radiation fields of the first stars. This pressure triggers a burst of rapid, efficient star formation, packing millions of stars together into a tight, gravitationally bound ball. This scenario fits well with the idea of clusters forming within the massive, turbulent gas clouds that were building large galaxies. But a dwarf spheroidal galaxy like Fornax is the antithesis of a high-pressure environment. It is a low-density, quiescent system that has likely never experienced the violent, large-scale star-forming events thought to be necessary. So how did it manage to create such impressive clusters? One compelling possibility is that the relationship we see in the modern universe is misleading. Perhaps in the intense early universe, the process of forming a globular cluster was actually much easier, or at least more common, than it is today. The pristine gas that filled the cosmos after the Big Bang may have had physical properties that made it more prone to fragmenting directly into dense, massive star clusters, regardless of the size of the dark matter halo it was residing in. In this view, the Fornax dwarf spheroidal galaxy might have simply been a lucky site that captured a large reservoir of this primordial gas, allowing it to form its brilliant clusters during a universal window of opportunity that quickly closed. The galaxy itself never grew to a large size, but it retained the magnificent clusters it formed in that initial burst, like a family heirloom passed down through generations. Another, more dramatic explanation involves the brutal history of galaxy interactions. It's possible that the Fornax dwarf galaxy was not always so small and quiet. In the past, it could have been a much more substantial galaxy that underwent a close encounter with a larger neighbor, perhaps the central galaxy of the Fornax cluster. During such a gravitational tidal encounter, the outer, diffuse stars of the smaller galaxy can be easily stripped away, leaving behind only its resilient, densely packed core and its tightly bound globular clusters. What we see today as the dwarf spheroidal galaxy, with its surprisingly rich cluster system, might therefore be the stripped-down remnant of a formerly grander galaxy. The clusters are not overachievers for the galaxy's current size. Rather, the galaxy has been downsized around them, its outer layers peeled back to reveal a cluster system that was once appropriate for a larger parent. This would make the Fornax system a striking example of galactic archaeology, where the clusters serve as fossils pointing to a more massive and dramatic past. The enigma of the Fornax clusters is more than a simple curiosity. It is a direct challenge to our understanding of galaxy evolution. By studying this system, we are forced to ask whether the current properties of a galaxy reliably record its entire history, or if we are often looking at the ghost of a former self. The bright, numerous clusters of this faint galaxy stand as a testament to a more vigorous era, their continued presence a silent question about the true conditions of the early universe and the violent processes that have shaped the galaxies we see today. The quiet, steady evolution of stars within a globular cluster tells only part of the story. When we shift our view from the calm glow of visible light to the high-energy realm of X-rays, a completely different and far more violent picture emerges. Telescopes designed to see this energetic radiation have revealed that these ancient star clusters are veritable hotbeds of intense activity, hosting a disproportionately large number of exotic objects known as low-mass X-ray binaries. To find one of these systems is remarkable. To find them in such abundance within globular clusters is a clear signal that the unique environment of a cluster is a factory for creating cosmic oddities that are rare elsewhere in the galaxy. So, what exactly is a low-mass X-ray binary? It is a partnership between two stars in a gravitational dance, but a partnership with a very one-sided and destructive relationship. One member of the pair is a compact stellar remnant, either a neutron star or a stellar mass black hole. This object is the gravitational heavyweight, the product of a past supernova explosion. Its companion is an ordinary low-mass star, similar to our Sun or even smaller. If these two objects are orbiting close enough, the immense gravity of the dense remnant begins to violently strip material away from the outer layers of its larger, but more diffuse companion. This stolen gas doesn't fall directly onto the neutron star or black hole. Instead, it forms a swirling, hot disk of material called an accretion disk. As the gas spirals inward, it is compressed and heated to temperatures of millions of degrees, causing it to glow brilliantly in X-rays, outshining the entire cluster in this high-energy light. This is the signature of an X-ray binary, a beacon of intense radiation powered by cosmic cannibalism. The puzzle is not how these systems work, but why they are so common in globular clusters. In the general field of the Milky Way, where stars are widely separated, the formation of such a tight binary system is a matter of chance. Both stars would need to be born as a close pair, and the more massive one would have to go supernova without completely disrupting the system with its explosive kick. This is a rare sequence of events, but in a globular cluster, the rules of stellar dating are completely rewritten by the sheer density of stars. The crowded core acts as a gravitational mixer, where close encounters between stars are not rare accidents but frequent, expected events. A solitary neutron star drifting through the chaos can quite easily have a close gravitational interaction with an unrelated, ordinary star system. During this encounter, the complex dance of gravity can bind the two objects together or even trade partners, ejecting one star from a pre-existing binary and replacing it with the neutron star. This process, known as dynamical formation, is the primary reason for the proliferation of these exotic binaries. The cluster itself acts as a matchmaker, forcing stellar encounters that would never happen in the solitude of the galactic disk. This dynamical creation of X-ray binaries is just one example of a broader class of stellar exotica that thrive in dense environments. A closely related phenomenon is the cataclysmic variable. These systems operate on a similar principle but involve a white dwarf, the Earth-sized core of a star like our Sun, as the gravitational predator, accreting material from a close companion. The result is not a steady X-ray glow, but a series of violent outbursts. As enough hydrogen-rich gas accumulates on the surface of the white dwarf, it can suddenly ignite in a runaway thermonuclear explosion, causing the system to flare up dramatically in brightness for a period of days or weeks before fading away. These recurring nova are another testament to the dynamic social life within a cluster, where stellar interactions frequently create these volatile partnerships. The high stellar density does more than just create these systems, it also dictates their lifespan and location. The same dynamical encounters that form a binary can also eventually tear it apart. A particularly close pass by another star can disrupt the delicate balance of the system, either widening the orbit to stop the accretion process or ejecting one of the stars entirely. This means that the population of X-ray binaries we observe today represents a steady-state balance between creation and destruction. Furthermore, through a process called dynamical friction, the heaviest objects, including these binary systems with their dense neutron stars or black holes, tend to sink toward the very center of the cluster over time. This is why astronomers often find the highest concentration of these energetic sources right in the cluster's core, a central powerhouse of high-energy activity that belies the cluster's serene appearance in visible light. The prolific number of X-ray binaries is therefore a direct and observable consequence of the relentless gravitational interactions that define life in these ancient stellar cities, proving that their quiet retirement home appearance is merely a facade for a deeply dynamic and occasionally violent reality. Just when we think we have the life story of a globular cluster neatly mapped out, born in a frantic burst in the early universe, aging quietly for billions of years, the cosmos presents us with a brilliant exception that forces us to rewrite the entire narrative. This exception lies not within our own Milky Way, but in our galactic backyard, a satellite galaxy known as the Large Magellanic Cloud. For centuries, this hazy patch in the southern sky was simply a curious neighbor. But when astronomers pointed the full power of modern telescopes like Hubble towards it, they found something that should not, according to our old textbooks, exist at all. Young, massive globular clusters, shining with the brilliance of youth in a universe that is predominantly old. The traditional definition of a globular cluster was inextricably linked to extreme age. They were the senior citizens of the cosmos, all dating back to a specific window of time shortly after the Big Bang. The reasoning was that the conditions needed to form such densely packed balls of stars' incredible gas pressure and the absence of heavier elements that can disrupt cloud collapse were only prevalent in the violent, pristine early universe. That era ended, the universe evolved, and the formation of new globular clusters was thought to have ceased. The ones we see today were considered the last of their kind, fossils from a bygone age. The Large Magellanic Cloud shatters this comfortable assumption. Here we find spectacular clusters like NGC 1818 and NGC 1850. These are not ancient relics. Spectroscopic analysis of their starlight reveals they are mere infants in cosmic terms, only 1 to 3 billion years old. To put that in perspective, when the oldest globular clusters in our halo were already 10 billion years old, the light from the very first stars in these LMC clusters was just beginning its journey across space. What makes these young clusters so revolutionary is that they are not just loose, open associations of stars. They possess all the classic hallmarks of a true globular cluster. They are massive, containing hundreds of thousands or even millions of stars, and they are spherical and gravitationally bound, destined to last for tens of billions of years. They are, in every structural sense, identical to their ancient cousins, but they carry a youthful vibrancy that we never thought possible. Their brightest stars are massive, blue, and brilliant, having not yet had time to evolve and die. Their color magnitude diagrams look completely different from those of ancient clusters, bursting with the light of short-lived stellar giants. Their existence proves that the recipe for building a globular cluster is not a secret lost to the early universe. It is a process that can, under the right conditions, be replicated much later in cosmic history. So what are those special conditions? Why did the Large Magellanic Cloud succeed in building these impressive structures long after our own galaxy had stopped? The answer lies in the dynamic and tumultuous life of this smaller galaxy. Unlike the Milky Way, which has enjoyed a relatively sedate evolution, the Large Magellanic Cloud has experienced a much more eventful past. It is currently undergoing a significant gravitational interaction with both the Milky Way and its close companion, the Small Magellanic Cloud. These interactions are not gentle. They are cosmic earthquakes that send massive shockwaves through the galaxy's vast reservoirs of gas. When giant molecular clouds are compressed by these external tidal forces, the result is a dramatic increase in pressure, triggering epic bursts of star formation. This is the key ingredient that was missing from the more settled environment of the modern Milky Way: extreme external pressure. In essence, the Large Magellanic Cloud has recreated the violent conditions of the early universe through galactic collisions. The process mirrors what we think happened 13 billion years ago, but on a local scale. A giant molecular cloud, compressed and agitated by a close galactic encounter, collapses under its own gravity. The star formation that follows is not a slow, steady trickle but a furious firestorm, producing hundreds of thousands of stars in a short period. Because the event happens so quickly and within a confined volume, the stars remain bound together by their collective gravity, forming a new globular cluster. This discovery transforms our understanding from a simple timeline into a conditional recipe. It's not about when you form a cluster, it's about how. Any galaxy at any time can create a globular cluster if it experiences the kind of dramatic, gas-compressing event that provides the necessary trigger. The implications of this are profound. It suggests that the census of globular clusters around a galaxy is not just a marker of its age, but a living record of its most violent interactions. The presence of young globular clusters in the Large Magellanic Cloud is direct evidence of its recent turbulent history. Furthermore, it opens up the possibility that other galaxies, particularly those in dense cluster environments where collisions are frequent, may also be producing new globular clusters today. This moves these objects from the realm of static fossils into the category of active, evolving entities. The young clusters of the LMC are more than just beautiful anomalies. They are a vital clue, demonstrating that the universe still holds the power to create its most majestic structures and that the story of star formation is far from over. The crowded environment of a globular cluster, which creates stellar vampires and cosmic cannonballs, also fosters a surprisingly social stellar lifestyle. While our own Sun is a solitary star, the opposite is true within these dense stellar cities. Astronomers have discovered that a remarkably high fraction of stars in globular clusters are not single like our Sun, but exist in pairs or even triple systems bound together by gravity in an eternal dance. This abundance of binary star systems is far greater than what we find in the common galactic neighborhood, and it turns out that these paired stars are not just a curiosity. They are absolutely essential to the very survival and stability of the cluster itself. They act as a gravitational energy source, a cosmic regulatory system that prevents the cluster's core from catastrophically collapsing in on itself. To grasp why this is so vital, picture the core of a cluster as a gravitational battlefield. With so many stars packed into a relatively small volume, they are constantly interacting, their paths altered by the pull of their neighbors. Over billions of years, a fascinating process called dynamical evolution takes place. Through a series of gravitational encounters, energy is exchanged between stars. The general trend is for the most massive stars to lose kinetic energy and sink toward the center, while lighter stars gain energy and migrate outward. Without a mechanism to counteract this, the core would become denser and denser, the stellar traffic jam worsening until the stars at the very heart were in danger of colliding and merging in an uncontrollable chain reaction, leading to a state known as core collapse. This is where binary stars become the heroes of the story. Think of a binary system not as two separate stars, but as a single, complex gravitational entity with a significant store of internal energy. When a lone, single star passes relatively close to this binary pair, a sophisticated three-body gravitational interaction occurs. The motions are complex, but the net result is often that the single star gets a gravitational slingshot, receiving a burst of energy that sends it flying outward into the cluster's halo at a higher speed. To conserve energy, the binary system itself must lose an equivalent amount of energy, causing its orbit to tighten slightly. In this single encounter, gravitational potential energy stored in the binary's orbit has been converted into kinetic energy for the single star. This process is like winding up a spring and then releasing it to propel an object away. Now, imagine this happening not once, but millions of times over the lifetime of a cluster. Each interaction acts as a gravitational energy transfer, effectively pumping heat from the core out to the halo. The single stars that get kicked outward act like a cooling system, carrying excess energy away from the densely packed center and preventing it from overheating, gravitationally speaking. This constant churn of energy exchange acts as a thermostat, regulating the core's density and preventing it from reaching the extreme state of collapse. In clusters where the fraction of binary stars is high, this stabilizing effect is powerful enough to maintain a balanced structure for eons. The binary stars are, in effect, the beating heart of the cluster's dynamical engine, their intricate dances providing the necessary energy to keep the entire system from imploding. The implications of this are profound. It suggests that a globular cluster's long-term fate is not just a matter of its initial mass and density, but is critically dependent on its population of binary stars. A cluster that forms with a rich community of stellar pairs has a built-in safety mechanism, a source of gravitational fuel that can sustain it for much longer against the relentless pull of gravity. In contrast, a cluster with very few binary systems would be far more susceptible to core collapse, potentially leading to a much more dramatic and rapid evolution. This binary star conundrum, their unexpected prevalence and their crucial role, transforms our view of these clusters from simple collections of stars into complex, self-regulating ecosystems, where the social interactions between stars ultimately dictate the grand architecture and longevity of the entire celestial city. This sharp turn in the stellar census, this characteristic knee, is far more than just a statistical curiosity. It is a direct window into the most common fate for stars in the universe, and it provides astronomers with one of the most reliable cosmic yardsticks ever discovered. To understand why this feature appears, we need to follow the life cycle of the vast majority of stars in a cluster. Most stars are not brilliant, massive giants. They are modest, sun-like stars or even smaller red dwarfs. After spending billions of years burning hydrogen steadily on the main sequence, a star like our Sun eventually exhausts the fuel in its core. It swells into a red giant, then, in a final, beautiful act, it gently sheds its outer layers into space, creating a glowing planetary nebula. What remains is the star's incredibly dense, Earth-sized core, a white dwarf. No longer powered by fusion, this stellar ember possesses a tremendous amount of residual heat, glowing white-hot from its formation. But with no new energy source, it has only one path forward, a long, slow, and predictable fade into darkness. This cooling process is the key to the luminosity function's need. For the first part of a white dwarf's life, its cooling follows a relatively steep curve. It loses heat quickly and its brightness drops at a rapid rate. This creates a steady stream of white dwarfs piling up at the brighter magnitudes on the graph. However, after about 1 to 2 billion years of cooling, a fundamental physical change occurs within the dwarf. The interior, once a seething plasma, begins to crystallize, starting from the core and moving outward. This phase transition, much like water turning to ice but involving carbon and oxygen under incredible pressure, releases latent heat. This injection of energy acts as a cosmic brake, significantly slowing the white dwarf's rate of cooling. Consequently, the white dwarfs spend a much longer time at this specific, fainter luminosity. On the graph, this manifests as a sudden pile-up, a sharp excess of white dwarfs at a distinct magnitude, the knee. The brilliance of this knee as a tool is its predictability. The physics of white dwarf cooling is extremely well understood. It is a straightforward process of thermal emission that depends primarily on the object's mass and composition. Because all the white dwarfs in a given globular cluster are virtually the same age and have similar chemical makeup, their cooling sequences are nearly identical. This means that the absolute magnitude, the true, intrinsic brightness of the knee is effectively a constant. It's a standard candle, but one that is not a single star but a statistical feature of an entire population, making it far less susceptible to errors than relying on individual variable stars. To measure the distance to a cluster, astronomers simply observe the apparent brightness of the knee, how dim it looks from Earth, and compare it to its known absolute brightness. The difference between the two directly reveals the vast distance the light has traveled, providing a measurement of remarkable precision. This method has become a cornerstone of the cosmic distance ladder, offering a crucial independent check on other techniques like those using variable stars. But the knee's utility doesn't stop there. It also serves as a sensitive probe of the cluster's age and its stellar physics. The location of the knee on the luminosity function is directly tied to the age of the white dwarf population, which in turn is tied to the age of the cluster's main sequence turn-off. By modeling the cooling process and matching it to the observed position of the knee, astronomers can derive an age estimate for the cluster that is entirely independent of the main sequence method, helping to resolve uncertainties like the age paradox we discussed earlier. Furthermore, subtle deviations in the shape of the knee can reveal information about the internal composition of the white dwarfs or even hint at the presence of exotic physics, such as actions, hypothetical particles that could provide an additional cooling channel. In this way, a simple statistical feature in the starlight of a distant cluster becomes a multifaceted instrument, allowing us to measure the scale of the universe, date its oldest structures, and test the fundamental laws that govern matter itself. While the steady glow of white dwarfs reveals the internal structure of a cluster, an even more subtle effect allows these dense collections of stars to act as cosmic telescopes, revealing objects that would otherwise be permanently hidden from our view. This phenomenon is one of the most remarkable predictions of Einstein's theory of general relativity, gravitational lensing. The theory tells us that mass warps the fabric of space-time, and as light travels through this warped geometry, its path is bent, much like a glass lens bends light. A massive object like a galaxy cluster can create a powerful lens, producing dramatic arcs and multiple images of a single, distant galaxy. But on the smaller, yet still immensely significant, scale of a globular cluster, a different and exquisitely sensitive version of this effect takes place, known as microlensing. Imagine a single star in a globular cluster, thousands of light years away, drifting silently through space. Now, imagine a much more distant star, perhaps located in the galactic bulge tens of thousands of light years behind it. From our vantage point on Earth, these two stars are nearly perfectly aligned. As the foreground star in the cluster moves across the sky, its gravitational field creates a temporary, tiny warp in spacetime. When the light from the background star passes through this warp, it is focused and amplified, causing the distant star to appear temporarily brighter. This is not a magnification of the star's surface like a zoom lens. It is an amplification of its entire light output. The effect is fleeting, typically lasting from a few hours to a few days, as the constant proper motion of the cluster star carries it out of alignment. There is no distortion or multiple images. There is only a smooth, predictable brightening and subsequent fading of the background source, a cosmic flashbulb triggered by gravity itself. The power of microlensing lies in its utter indifference to the brightness of the lensing object. It does not matter if the star in the globular cluster is a brilliant giant or a faint, nearly invisible brown dwarf. If it has mass, it can act as a lens. This makes microlensing an unparalleled tool for detecting the dark, unseen members of a cluster. For every shining star we can count, there is likely a population of faint stellar remnants, white dwarfs, neutron stars, and black holes, and even a host of planet-sized objects that emit little to no light. These dark objects are effectively invisible to direct observation, but when one of them passes in front of a background star, its gravitational influence betrays its presence through the characteristic microlensing flare. By monitoring millions of background stars in the crowded fields toward the galactic center, and watching for these subtle, transient brighten events that align with the position of a globular cluster, astronomers can conduct a gravitational census of the cluster's dark content, weighing its invisible constituents directly. This technique has yielded spectacular results, most famously in the discovery of planets within the cluster M4, which we discussed earlier, but its applications go far beyond hunting for individual worlds. By statistically analyzing the rate and duration of microlensing events observed toward a cluster, astronomers can estimate the total mass locked away in these compact, dark objects. This provides a crucial check on our models of cluster evolution. Does the mass inferred from the motions of visible stars match the mass revealed by the microlensing census of dark objects? The answer helps us understand the complete life cycle of stars within the cluster, telling us how many have ended their lives as faint remnants and how that population contributes to the cluster's overall gravitational field. It is a way of seeing the invisible skeleton that holds the glittering body of the cluster together. Furthermore, microlensing turns the entire cluster into a natural amplifier, allowing us to study background stars with a level of detail that would be otherwise impossible. When a distant, faint star is magnified by a factor of 10 or even 100, its light becomes bright enough to analyze with a high-resolution spectrograph. For a brief window, we can obtain a detailed chemical fingerprint of a star that is far too remote to study directly, probing the composition of stellar populations in the galactic bulge or even in other galaxies. In this way, the globular cluster ceases to be just an object of study and becomes an active partner in our exploration, its gravitational field providing a fleeting but powerful lens that brings the distant universe into sharp, brilliant focus, revealing secrets both within its own boundaries and far beyond them. Yet another layer of mystery is revealed when we take a census of the stellar populations within these ancient clusters and find that the expected residents are simply not there. This brings us to a subtle but deeply puzzling observation known as the missing red giants problem. To understand why this is so strange, we need to revisit the standard life cycle of a star like our Sun. After spending billions of years fusing hydrogen in its core, such a star eventually exhausts that central fuel. At this critical juncture, it begins a dramatic transformation. With fusion ceasing in the core, the star can no longer support itself against its own gravity. The core begins to contract and heat up, while the outer layers expand outward to a tremendous size, cooling as they go. The star swells into a red giant, becoming hundreds of times larger and thousands of times more luminous than it was on the main sequence. For a star cluster, this evolutionary phase is a cornerstone of our theoretical models. We expect to see a well-populated branch of red giant stars, a clear and prominent feature on any color magnitude diagram representing an ancient stellar population. However, when astronomers pointed their telescopes toward the cores of certain globular clusters, particularly those with the highest densities like Messier 30, they found a curious discrepancy. The number of red giant stars observed in the central regions was significantly lower than what the models predicted. It was as if a specific demographic of the stellar population had vanished from the most crowded neighborhood. These stars had successfully evolved off the main sequence. They were on the path to becoming red giants, but somewhere along that journey, within the intense environment of the cluster core, their evolution was being cut short. They were reaching the red giant branch, but then they seemed to be disappearing before their time. This was not a small statistical fluke. It was a consistent anomaly that pointed directly to the core's extreme conditions as the culprit. The leading hypothesis for this vanishing act centers on the perilous reality of life in a dense stellar environment. A red giant is by its very nature a vulnerable object. It is a star that has puffed itself up to an enormous size, its outer layers becoming tenuous and loosely bound by gravity. Now place this fragile, inflated star into the chaotic gravitational field of a cluster core, where close encounters with other stars are a regular occurrence. The consequences could be dramatic. One possibility is direct stellar collision. While the spaces between stars are vast, the relative velocities in a cluster core are high, and the cross-section of a red giant is enormous. A collision with another star, or even a very close pass, could strip away a significant portion of the red giant's distended outer envelope. This would effectively rob the star of the material it needs to sustain its giant phase, prematurely ending its life as a luminous giant and leaving behind only its hot, dense core, a helium-burning star that would appear much bluer and fainter than the red giant it was supposed to become. Another, more subtle mechanism involves the relentless gravitational tides. Even without a direct impact, the repeated gravitational tugs from passing stars can act like a constant peeling force on the red giant's loosely held atmosphere. Over time, this tidal stripping could gradually erode the outer layers, again truncating the star's evolution. There is also the fascinating role of binary companions. If the evolving star is part of a close binary system, its expansion into a red giant can lead to it filling its Roche lobe, the region around a star where material is gravitationally bound to it. Once it expands beyond this point, mass will stream onto its companion. This process can strip the giant of its hydrogen-rich envelope at an accelerated rate, dramatically altering its path across the color magnitude diagram. Instead of ascending the red giant branch, the star might be redirected onto a completely different evolutionary track, appearing as a much hotter and less luminous object. The implication of the missing red giants is profound. It suggests that the very environment of a globular cluster can actively edit the standard textbook story of stellar evolution. The fate of a star is not determined solely by its mass and initial composition. It is also shaped by its social environment. In the crowded core, the gentle, predictable aging process of a solitary star can be violently interrupted by gravitational interactions. This discovery forces astronomers to refine their models, incorporating these dynamic effects to accurately predict the populations we observe. The missing red giants are a silent testament to the hidden dramas unfolding in the hearts of these clusters, where the peaceful journey of a star can be abruptly rewritten by a close encounter, leaving a gap in our observations that speaks volumes about the invisible forces at work. And now we arrive at a mystery that connects these ancient star clusters to one of the most electrifying enigmas in modern astronomy: fast radio bursts. Picture this: a flash of radio waves brighter than 500 million suns, lasting for only a few thousandths of a second, and then it's gone. These are fast radio bursts, or FRB. They erupt from the distant cosmos, and for over a decade, their origin has been one of the most sought-after prizes in astrophysics. The energy released in a single millisecond is staggering, equivalent to what our sun puts out over several decades. The question is, what natural cosmic engine could possibly produce such an immense, fleeting blast? For a long time, the suspects were exotic and extreme: merging neutron stars, evaporating black holes, or even signals from advanced alien civilizations. But a compelling and surprising candidate has emerged from an environment we are already familiar with: the dense, dynamic hearts of globular clusters. The link between FRBs and globular clusters is not as far-fetched as it might seem. In fact, it hinges on a specific type of stellar remnant that we know thrives in these crowded environments: the magneta. A magneta is a neutron star on steroids. It's the ultra-dense corpse of a massive star, but it possesses a magnetic field so powerful it defies comprehension, a quadrillion times stronger than Earth's field. A magnetic field of that magnitude is a storehouse of unimaginable energy. If the crust of a magneta were to undergo a sudden shift, a starquake, it could release a catastrophic blast of energy in the form of gamma rays and radio waves. This phenomenon, known as a soft gamma repeater burst, is a known cousin to FRBs. In 2020, a magneta within our own Milky Way galaxy was observed producing an FRB-like burst, providing the first solid evidence that these objects are indeed capable of such eruptions. So, if magnetas can make FRBs, the next logical question is, where do we find magnetas? This is where globular clusters enter the picture with a compelling advantage. We've already seen that these environments are factories for neutron stars, including millisecond pulsars. The same dynamical processes that create those pulsars, stellar collisions and binary interactions, are also perfect for creating magnetas. A magneta is thought to be the product of a particularly massive progenitor star, or crucially, the result of a merger between two neutron stars. And what environment is more conducive to stellar mergers than the chaotic core of a globular cluster? The frequent close encounters dramatically increase the odds of such a rare event. Therefore, it's entirely plausible that globular clusters could host a population of these magnetic monsters. When one of them has a starquake, the resulting FRB would be beamed across the universe. The cluster itself provides the ideal breeding ground for the very engine that could power these mysterious blasts. But the evidence goes beyond mere speculation. In 2020, astronomers made a landmark detection. They localized a repeating fast radio burst known as FRB 20201124A to a region within a galaxy that contained, you guessed it, a globular cluster. This was a stunning revelation. Before this, most localized FRBs had been traced back to the spiral arms of galaxies, regions of active star formation where young, massive stars live and die quickly. Finding an FRB source in a globular cluster was a paradigm shift. It pointed to an entirely different formation channel, one that operates in an ancient, stable environment rather than a youthful, chaotic one. This single observation forced a major rethink of FRB origins, suggesting that the long-lived, dense stellar cities we've been exploring are capable of producing these extreme events billions of years after their primary star-forming epoch ended. The implications of this connection are profound. If globular clusters are indeed significant sources of FRBs, it could help explain one of their lingering mysteries: why some bursts repeat while others are one-off events. A magnetar in a cluster, periodically experiencing starquakes as its immense magnetic field rearranges itself, would naturally produce repeating bursts. Furthermore, the dense environment could influence the properties of the signal itself. The radio waves from an FRB have to travel through the ionized gas within the cluster before escaping into intergalactic space. This journey could imprint a specific signature on the signal, a subtle fingerprint that astronomers could use to identify a cluster origin for other, more distant FRBs. The hunt is now on to find more of these links. By focusing new radio telescopes on nearby globular clusters, scientists are listening intently, hoping to catch the telltale millisecond chirp of an FRB originating from one of these ancient stellar metropolises. It's a breathtaking convergence of mysteries. The solution to one of the newest puzzles in the cosmos may be hiding within some of its oldest structures. This chemical complexity, particularly the enrichment of helium, doesn't just rewrite the cluster's history. It fundamentally alters the future of the stars themselves, creating a spectacle on the color magnitude diagram that is found nowhere else in the universe. After a star exhausts the hydrogen in its core and evolves into a red giant, it reaches a critical and brief phase in its life known as the horizontal branch. For a simple stellar population with a uniform chemical makeup, this phase is relatively straightforward. The star begins to fuse helium in its core, and for a short time, it achieves a kind of stability, settling into a specific location on the diagram based on its mass. You would expect all the stars of similar mass to clump together in a tight, neat group. But when astronomers look at the horizontal branches of globular clusters, they see something far more dramatic and beautiful, a spectacular spread. Instead of a compact point, the stars are scattered across a wide horizontal swath, with some appearing as hot, blue stars and others as cooler, red stars. This dispersion is the direct and stunning consequence of that second generation of stars being born with an extra helping of helium. The reason for this lies in the very core of stellar physics. Helium is heavier than hydrogen. In a star that has been enriched with extra helium, either from its birth cloud or through later accretion, this heavier element changes the star's internal structure in a profound way. When such a star finally exhausts its hydrogen fuel and begins its journey off the main sequence, the increased helium abundance makes its core more compact and dense. A more compact core burns hotter and more efficiently. When the star ignites helium fusion and settles onto the horizontal branch, this compactness has a direct effect on its outer layers. The star will have a smaller radius and a much hotter surface temperature compared to a star of the same mass but with a standard, lower helium composition. On the color magnitude diagram, a hotter surface temperature means a bluer color. So, a helium-rich star will appear on the blue side of the horizontal branch, while a star with a normal helium abundance will appear on the red side. The spread we observe is essentially a thermometer, measuring the varying degrees of helium enrichment across the stellar population. But the influence of helium goes beyond just color. It dramatically shortens the star's journey. Because a helium-rich star is hotter and burns its fuel more fiercely, its time on the horizontal branch is significantly reduced. It races through this phase of its life at a much quicker pace than its pristine counterparts. This creates a fascinating observational effect. The bluest, hottest stars on the horizontal branch, which are the most helium-enriched, are also the most ephemeral. They are the stellar mayflies, living a brilliant but brief life before evolving further into the final stages of their existence. This connection between chemistry and destiny is a powerful reminder that the initial ingredients of a star are the primary architects of its entire life story. The helium-rich second generation, born from the ashes of their predecessors, are not just chemically distinct, they are destined for a faster, hotter, and more fleeting evolution. This phenomenon reaches its most extreme expression in a mysterious group of stars that seem to defy the very edge of stellar evolution. In some clusters, astronomers have identified stars so blue and so hot that they appear to have jumped right off the expected evolutionary path. These blue hook stars are found at the extreme blue end of the horizontal branch, in a region where standard models suggest no star should exist. The leading theory to explain these stellar extremists involves a truly dramatic event, a late helium flash combined with a subsequent flash of helium fusion in the star's shell. In this scenario, the star's helium-rich core becomes so hot and dense that it undergoes a violent, explosive ignition of helium fusion rather than a quiet one. This flash can trigger a massive ejection of the star's remaining hydrogen-rich outer envelope. Stripped of this blanket, the star's hot, helium-burning core is exposed, rocketing its surface temperature to incredible heights and creating the brilliant blue hook star we observe. These objects are the ultimate expression of the chaotic influence of helium enrichment, showing us that the path of stellar life is not always smooth and predictable, but can be punctuated by violent internal events that radically reshape the star's appearance and fate. While the flash of an FRB represents a sudden, dramatic release of energy, the overall structure of a globular cluster is shaped by a far more gradual, yet relentless, gravitational process playing out over billions of years. This brings us to the very engine of a cluster's long-term evolution, its dynamical state, a concept that culminates in one of the most extreme phenomena in stellar astronomy, core collapse. To understand this, we need to envision a globular cluster not as a static sculpture, but as a living, breathing entity, a gravitational gas where the individual stars act like molecules in a constantly churning system. The key to this entire process is the fundamental principle of energy exchange. In any isolated system, there is a natural tendency to evolve toward a state of thermodynamic equilibrium, where energy is evenly distributed. For a star cluster, this means the collective gravitational energy of all its stars will seek a balance. The mechanism driving this evolution is a fascinating phenomenon known as two-body relaxation. In the crowded core of a cluster, stars are constantly whizzing past one another. Each close encounter, each gravitational tug, results in a tiny transfer of energy. It's a cosmic game of pool on an unimaginable scale. Over time, through millions of these gentle gravitational nudges, a clear trend emerges. On average, the more massive stars tend to lose kinetic energy and slow down, causing them to sink toward the center of the cluster's gravitational well. Meanwhile, the lighter stars tend to gain energy, speeding up and migrating outward toward the cluster's halo. This process, acting over billions of years, is like a gravitational centrifuge sorting the cluster's population by mass. The result is a gradual but steady increase in the density of the core, as the heaviest objects, stars, stellar remnants, and binary systems all drift inward. If this process continued unchecked, it would lead to a runaway scenario, core collapse. Imagine the core's density increasing to a point where the stars are so densely packed that their orbits become wildly unstable. The time between close encounters shrinks from millions of years to mere thousands. In this frantic environment, the gravitational interactions are no longer gentle nudges but violent, chaotic events. Stars can be flung out of the cluster entirely, or they can be sent on radial orbits that plunge them deep into the core and back out again. This runaway contraction can continue until the central density soars to astonishing levels, potentially hundreds of thousands of times greater than in the cluster's outskirts. In this state, the core is no longer a stable system. It is a gravitational pressure cooker on the verge of a catastrophic chain reaction where direct stellar collisions become not just possible but inevitable. However, nature has a built-in safety valve, and it comes from an unexpected source: binary stars. We've already seen how these paired systems are crucial for a cluster's health, and in the context of core collapse, they become the heroes of the story. As the core contracts and the stellar traffic jam worsens, the likelihood of a single star having a close encounter with a binary system skyrockets. When this happens, a complex three-body gravitational interaction occurs. The net result is often that the single star gets a tremendous gravitational slingshot, receiving a burst of energy that sends it flying out of the core at high speed. To conserve energy, the binary system must lose an equivalent amount of energy, causing its orbit to tighten. In this single encounter, gravitational potential energy that was stored in the wide orbit of the binary pair has been converted into kinetic energy for the single star, effectively heating the cluster. This process acts as a powerful regulatory mechanism. As the core collapses and the density rises, the rate of these binary-mediated encounters increases dramatically. This pumps a huge amount of energy back into the stellar system, halting the collapse and potentially causing the core to rebound and re-expand. It's a remarkable feedback loop. Gravity drives the core toward collapse, but the very interactions that collapse enables those involving binary stars generate the heat needed to reverse the process. This can lead to a cyclical behavior where a cluster's core undergoes phases of contraction and expansion over its multi-billion-year life. The presence of a sufficient population of binary stars is therefore critical to preventing a permanent, catastrophic collapse, acting as a gravitational energy source that keeps the core from turning into an infinitely dense singularity of stars. The observable signature of a cluster in a post-collapse or collapsing state is a steeply rising density profile toward the center. When astronomers map the distribution of stars in a cluster like Messier 15, they see this dramatic cusp, a clear indicator of its advanced dynamical age. This doesn't mean the cluster is about to vanish. It means it has passed through a major evolutionary milestone. The study of core collapse is not just about a single event, it's about understanding the life cycle of these stellar cities. It reveals that their serene, glittering appearance is a snapshot in a continuous dance of energy exchange, where the collective gravity of countless stars orchestrates a slow-motion drama of contraction and rebirth, ensuring that no cluster is ever truly at rest. While the globular clusters of our own Milky Way present a gallery of cosmic mysteries, to gain a truly universal perspective, we must cast our gaze beyond our galactic borders to our nearest large neighbor, the great Andromeda Galaxy. There, floating within its vast halo, we find an object so extraordinary that it challenges the very definition of a globular cluster. Known as G1 or Mayol 2, this celestial giant is not merely a star cluster. It is a behemoth, a gravitational titan that stands apart from the hundreds of thousands of clusters catalogued across the universe. With a mass surpassing 10 million times that of our Sun, G1 is several times more massive than the largest cluster in the Milky Way, Omega Centauri. Its sheer scale places it in an ambiguous category, blurring the line between a supremely massive star cluster and the stripped-down core of a small galaxy that Andromeda devoured long ago. The real revelation about G1, however, came from a meticulous study of the motions of its constituent stars. Using the Hubble Space Telescope, astronomers performed a detailed census, measuring the velocities of stars swirling around its core. The results were unambiguous and electrifying. The stars at the very heart of G1 were moving at such tremendous speeds that their motion could only be explained by the gravitational influence of a single, incredibly massive object. The calculations pointed to a central black hole weighing in at a staggering 20,000 solar masses. This was not a tentative hint or a disputed finding. It was the clearest, most robust evidence ever obtained for the existence of an intermediate mass black hole, the long-sought missing link between stellar mass black holes and the supermassive monsters that dominate galactic centers. G1 did not just suggest these objects might exist, it placed one on a cosmic scale for all to see. The presence of this black hole in G1, contrasted with their apparent absence in most Milky Way clusters, is a puzzle of galactic proportions. Why does this particular cluster possess such a definitive anchor when our own seemingly similar clusters do not? The most compelling explanation circles back to G1's extraordinary mass and its extragalactic origin. It is possible that G1 is not a true globular cluster in the sense that we understand them, but rather the surviving nucleus of a dwarf galaxy that ventured too close to Andromeda billions of years ago. In this scenario of galactic cannibalism, the tidal forces of the larger galaxy would have relentlessly stripped away the dwarf's outer stars, leaving behind only its dense, resilient core, which we now call G1. The black hole, as the central engine of that original galaxy, would have remained a permanent testament to its host's former independence. This makes G1 a direct parallel to M54 in our own halo, but on an even grander, more massive scale. Studying G1 is like being given a preview of the ultimate fate of Omega Centauri, the most massive cluster in the Milky Way, which is also suspected of being a captured core. By comparing these two colossal objects, astronomers can test theories about how such systems form and evolve. Does the relationship between the total mass of the cluster and the mass of its central black hole follow a predictable rule? How does the presence of a massive black hole influence the long-term dynamical evolution of the stars around it? G1 serves as a critical benchmark, a natural laboratory in another galaxy that allows us to perform comparative astronomy. It demonstrates that the processes of hierarchical growth through mergers are not limited to giant galaxies. They also apply to the smaller, denser building blocks of the cosmic landscape. The magnificent G1, therefore, is more than just a record holder. It is a key that helps unlock the evolutionary history of two great galaxies, revealing the violent and transformative encounters that have shaped them both. The bizarre chemical fingerprints we find in cluster stars, rich in sodium and helium but poor in oxygen, tell a story of stellar life and death. But when we look even closer at this cosmic chemistry, we uncover a puzzle that reaches back to the very first minutes of the universe, involving the most fragile elements in existence. This brings us to the origin of the lightest elements, lithium, beryllium, and boron. These elements are the delicate cosmic middle children caught between the primordial giants and the stellar powerhouses. They are too heavy to have been forged in the Big Bang, which produced almost no elements beyond hydrogen and helium, and they are too light to be cooked up in the nuclear furnaces of ordinary stars. In fact, attempting to fuse hydrogen into beryllium inside a star is a futile process. It's so unstable that any nucleus that forms almost instantly falls apart. So, if stars cannot make them, and the Big Bang barely produced them, where did these fragile elements come from? The answer may lie in the violent, high-energy environment of a young globular cluster through a process known as spallation. Spallation is essentially cosmic fragmentation. It occurs when a high-energy atomic nucleus, a cosmic ray, traveling at nearly the speed of light, smashes directly into a heavier, slower-moving nucleus like that of carbon or oxygen. The collision is so violent that it shatters the target nucleus into pieces, much like a sledgehammer hitting a ceramic pot. These fragments are the light elements, lithium, beryllium, and boron. They are the broken shards of a larger atomic structure. This process is the opposite of the fusion that powers stars. Instead of building elements up, it breaks them down. In the calm, sparse environment of the galactic disk, spallation is a slow and inefficient process. The cosmic rays are spread thin, and the chances of a high-speed proton colliding with a carbon nucleus are relatively low. But in the early, dense environment of a forming globular cluster, the conditions for spallation would have been perfect. Imagine the scene in the first few million years of a cluster's life. The first generation of massive stars has just been born. These stars are not just shining, they are living violently, producing fierce stellar winds, and when they die, exploding as supernova. These cataclysmic events do two things crucial for spallation. First, the supernova shockwaves act as natural particle accelerators, flooding the surrounding space with an intense, concentrated bath of high-energy protons and other atomic nuclei, a torrent of cosmic rays. Second, the explosions themselves spew out freshly synthesized heavier elements like carbon and oxygen, seeding the surrounding gas with the perfect targets for these cosmic rays to hit. Now confine this entire chaotic system within the dense, gaseous womb of the young cluster. The cosmic rays produced by the first supernova don't have far to travel before they encounter the newly formed carbon and oxygen nuclei lingering in the cluster's gas. The probability of a high-energy collision skyrockets in this confined, target-rich environment. This makes a young globular cluster a potential factory for these elusive light elements. The lithium, beryllium, and boron produced in these violent collisions would then be mixed into the reservoir of gas from which the second generation of cluster stars would form. When those stars ignited, they would have incorporated these spallation-produced elements into their atmospheres from birth. Therefore, if we could measure an enhanced abundance of these light elements in the second-generation stars of a cluster compared to the pristine first generation, it would be a smoking gun, direct evidence that this high-energy process was at work in the cluster's tumultuous youth. It would mean that the cluster was not just a site of stellar nucleosynthesis, but also a site of nuclear fragmentation, a place where the building blocks of the universe were both forged and shattered. However, detecting this signature presents a monumental challenge. Lithium is particularly tricky because it is a fragile element that is easily destroyed in the hot interiors of stars. As a star ages, convection can drag surface lithium down into the hotter layers where it is fused into helium. Therefore, the lithium abundance we measure on the surface of an old star may not reflect its original birth value. To see the true primordial or spallation-produced lithium, we need to look at the youngest, least evolved stars or at the outer atmospheres of stars where convection hasn't reached. Furthermore, beryllium and boron are exceedingly difficult to detect because their spectral signatures lie in the ultraviolet part of the spectrum, which is largely absorbed by Earth's atmosphere. This requires observations from space-based telescopes like Hubble. Despite these hurdles, the hunt is on. Finding this chemical signature would not only solve the mystery of the light elements in clusters, but would also provide a unique window into the extreme conditions present during the most dynamic and poorly understood phase of a globular cluster's life, its fiery birth. The grand cosmic dance of a globular cluster with its stellar collisions, binary interactions, and mysterious dark hearts might seem like it could continue forever. But like all things in the universe, these ancient cities of stars are subject to the relentless flow of time, destined for a fate that is as gradual as it is inevitable. Their story does not end in a single, spectacular explosion, but in a slow, quiet dissipation, a fading away that sees their stellar citizens gradually return to the wider galaxy from which they came. This dissolution is driven by two powerful and intertwined forces: the external pull of the galaxy itself and the internal dynamics of the cluster's own stellar population. The primary agent of this destruction is the galactic tide. As a globular cluster orbits its host galaxy, it is not moving through empty space but through the galaxy's gravitational field. Think of this field not as a uniform force but as a gradient. The side of the cluster closest to the galactic center feels a stronger gravitational pull than the side farther away. This difference in force, this tidal stress, constantly stretches the cluster, much like the Moon's gravity stretches the Earth's oceans. Each time the cluster makes its closest approach to the galactic center or passes through the dense plane of the galactic disk, it experiences a gravitational shock. These repeated tidal shocks act like a cosmic hammer, jarring loose the stars that are most weakly bound to the cluster, typically those in the outermost regions. Over the course of billions of years, this process slowly erodes the cluster, stripping it away layer by layer. The stars that are lost don't just vanish, they are gently pulled from the cluster's grasp and set onto their own independent orbits around the galaxy, becoming part of its vast, diffuse stellar halo. Internally, the cluster's own dynamics contribute to its gradual evaporation. We've seen how the constant gravitational encounters between stars lead to a process of energy exchange. While this helps regulate the core, it has a different effect on the cluster's outer edges. Through these interactions, some stars can gain enough kinetic energy to reach or even exceed the cluster's escape velocity. Imagine a complex gravitational slingshot between three stars. Two of them might end up in a tighter orbit, while the third is flung outward with such speed that it breaks free from the cluster's gravitational grip entirely. This process, known as evaporation, is a slow but steady leak of stars from the cluster. It's as if the bustling stellar city has a slow but constant emigration, with individual stars gaining their freedom and drifting off into the galactic wilderness. The rate of this evaporation is directly tied to the cluster's density and its orbital path. A cluster on a tight, punishing orbit around the galaxy will be stripped by tides far faster than a solitary cluster in the distant halo, but both will inevitably lose stars to this internal energy exchange. The breathtaking evidence of this ongoing destruction is written across the sky in the form of stellar streams. These are the ghostly remnants of clusters that have already been almost completely dismantled. They appear as long, faint rivers of stars arching through the galactic halo, all moving together on a shared trajectory. A stream like the one associated with the cluster Palomar 5 is a stunning example. The cluster itself is a faint, wispy object clearly on its last legs, but stretching away from it are two long, graceful tails of stars, pulled out by the Milky Way's tidal forces over many orbits. These streams are more than just celestial gravestones, they are incredibly sensitive probes. The very shape of a stream, its length, its width, any gaps or kinks within it records the gravitational history of the cluster. A smooth, symmetrical stream suggests a relatively peaceful orbital history, but a stream with a twist or a bend is like a fingerprint, evidence of a past close encounter with a dark matter subhalo or a dwarf galaxy, revealing the presence of invisible mass structures that we could never detect otherwise. So, what is the ultimate end? For many clusters, the journey concludes with complete dissolution. After tens of billions of years of tidal stripping and evaporation, the cluster will have lost so many stars that it can no longer hold itself together gravitationally. The remaining stars will drift apart, their shared motion fading until they are indistinguishable from the countless other stars in the galactic halo. The glittering city will have vanished, its former residents now scattered solo travelers in the vastness of the galaxy. This fate is not uniform, however. The most massive and tightly bound clusters, those that formed in the most dense environments, have a much better chance of survival. They possess a deeper gravitational well, making it harder for tides to pull stars away and for internal dynamics to fling them out. These cosmic titans, like Omega Centauri, may well survive for timescales that rival the age of the universe itself, potentially outliving their host galaxy in a future collision with Andromeda. This grand life cycle connects globular clusters directly to the building of the galaxy itself. The stars that are slowly being released from these clusters are not lost. They are being donated to the galactic halo, enriching it with a population of ancient metal-poor stars. In a very real sense, the ongoing destruction of globular clusters is a key mechanism in the growth and evolution of the galaxy's structure. They are cosmic seeders, dispersing their stellar inhabitants far and wide. This process reminds us that a galaxy is not a static collection of stars, but a dynamic, evolving ecosystem. The majestic globular clusters we admire today are temporary constellations, brilliant but fleeting features in the long narrative of the cosmos, their gradual fading a testament to the slow, powerful forces that shape the universe on the largest scales. While the idea of galactic cannibalism transforming a dwarf galaxy into a globular cluster might sound like a theory for the most distant reaches of the cosmos, we actually have a prime example of this process unfolding right in our own galactic backyard. This brings us to the crown jewel of the Milky Way's halo, a celestial wonder visible to the naked eye in the southern sky, Omega Centauri. To the casual observer, it appears as the largest and brightest globular cluster orbiting our galaxy, a magnificent fuzzy patch of light. But to astronomers, Omega Centauri is an imposter. It is a cosmic pretender, an object so massive, so complex, and so utterly unique that it simply cannot be explained by the standard model of globular cluster formation. It stands as the most compelling evidence that some of the most majestic objects we call clusters are, in fact, the fossilized hearts of long-dead galaxies. The first clue to Omega Centauri's extraordinary nature is its sheer scale. A typical globular cluster, like the magnificent M13, contains a few 100,000 stars. Omega Centauri, by contrast, is a stellar metropolis of nearly 10 million suns, making it 10 times more massive than its nearest rival in the Milky Way. Its gravitational pull is so strong that it has managed to hold onto its stars despite billions of years of galactic tides. But it's not just the number of stars that sets it apart, it's their bewildering diversity. We've already discussed how most clusters have multiple stellar populations, but Omega Centauri takes this to an entirely different level. Its stars exhibit a staggering range of ages and metallicities, the abundance of elements heavier than hydrogen and helium. While a normal cluster might show two distinct chemical groups, Omega Centauri's stars display a continuous spectrum, with some stars being almost as metal-poor as the Big Bang itself, and others showing significant enrichment, suggesting star formation occurred over a period of several billion years. This is not the signature of a single, frantic burst of star formation. It is the chronicle of a prolonged and complex evolutionary history, exactly what you would expect from a system that had its own independent life as a galaxy. The most definitive evidence, however, comes from the motions of its stars. When astronomers meticulously charted the velocities of stars within Omega Centauri, they discovered something unprecedented, not one but several distinct rotation patterns. The stars are not just swarming randomly in a gravitational ball. They are moving in a way that suggests the cluster still retains the dynamical memory of its galactic past. Different subgroups of stars appear to orbit the center on different planes and with different speeds, a complex kinematic structure that is completely unlike the simple, pressure-supported swarm of a genuine globular cluster. This is the ghost of a disk-like structure, a relic of the original dwarf galaxy's rotation that has not yet been completely erased by billions of years of dynamical evolution. All of these lines of evidence converge on a single, dramatic conclusion. Omega Centauri is not a true globular cluster. It is the stripped core of what was once a substantial dwarf galaxy that ventured too close to the youthful Milky Way. In this scenario, the original galaxy, which we might call the Omega Centauri progenitor galaxy, would have been a gravitationally bound system with its own dark matter halo, its own gas reservoir, and the ability to sustain star formation over an extended period. This explains the wide range of stellar ages and metallicities. As this small galaxy orbited the nascent Milky Way, the relentless tidal forces began to act like a cosmic cheese grater, gradually peeling away its outer layers of stars and dark matter. The loosely bound outskirts were shredded and scattered into the galactic halo, leaving behind only the most densely packed and gravitationally resilient part, the central bulge. What we see today as the brilliant globe of Omega Centauri is that surviving core, a trophy of one of the Milky Way's most ancient acts of galactic cannibalism. This reclassification transforms Omega Centauri from a spectacular object into a scientific treasure. It serves as a nearby laboratory for studying the final stages of galaxy disruption, a process that is happening all across the universe but is difficult to observe in detail elsewhere. It also raises a fascinating possibility about the mysterious missing red giants we discussed earlier. The complex gravitational field within this remnant core, still echoing with its galactic past, could be an additional mechanism for stripping the envelopes of giant stars, contributing to their apparent absence. Furthermore, the sheer mass of Omega Centauri makes it a prime candidate for hosting an intermediate mass black hole at its center, a relic of the black hole that would have anchored its original galaxy. While the search for this black hole continues, the very existence of Omega Centauri as a galactic fossil proves that the line between a massive star cluster and a small galaxy is often blurred, a testament to the violent and transformative history of our own Milky Way. But the influence of these ancient stellar cities extends far beyond their own boundaries, reaching out to shape the entire cosmos during its most formative era. This brings us to a discovery that positions globular clusters not as passive relics, but as active players in one of the universe's most profound transitions, the epoch of reionization. For hundreds of millions of years after the Big Bang, the universe was a dark, featureless sea of neutral hydrogen gas. Light from the very first stars and galaxies was trapped, their photons quickly absorbed by this thick primordial fog. Then, suddenly, over a period spanning from about 1 billion to 500 million years after the beginning, the entire cosmos was flooded with a transformative energy. Something happened to rip the electrons away from those neutral hydrogen atoms, turning the opaque fog into a transparent, ionized plasma, a state the universe has remained in ever since. The question of what provided the tremendous amount of ultraviolet radiation needed for this universal-scale cleansing has been one of cosmology's great puzzles, and the answer may lie in the concentrated fury of the first globular clusters. The challenge of reionization is one of sheer energy output. The photons required to ionize hydrogen are high-energy ultraviolet photons. To produce them, you need hot, massive, short-lived stars. But early galaxies, especially the small, faint dwarf galaxies that were the first to form, were not particularly efficient at producing and releasing this ionizing radiation. Much of the intense UV light from their massive stars would have been absorbed by the dense clouds of dust and gas within the galaxy itself, never escaping to affect the wider intergalactic medium. This is where the unique architecture of a globular cluster becomes a game-changer. A cluster forming in the early universe would have been a powerhouse of UV production, packing tens of thousands of massive, brilliant stars into an incredibly small volume. The sheer concentration of these stellar engines would create a collective radiation field so intense that it could effectively blow away the surrounding gas and dust that might otherwise trap the radiation. Imagine a single massive star as a powerful flashlight. Its beam is bright, but if it's shining through a dense fog, the light doesn't travel far. Now, imagine taking 10,000 of those flashlights and bundling them together into a single, colossal searchlight. The combined beam is so focused and powerful that it can blast a clear channel through the fog, allowing the light to travel vast distances. This is the effect a young globular cluster would have had on its local environment. The fierce stellar winds and radiation pressure from the concentrated population of massive stars would have carved out vast bubbles of ionized hydrogen around the cluster, creating transparent cavities through which the deadly UV photons could stream virtually unimpeded into intergalactic space. These clusters would have acted as pinpoint beacons of ionizing energy, their radiation punching far above the weight of their host dwarf galaxy. This hypothesis transforms our view of these objects from simple stellar collections into cosmic lighthouses that helped illuminate the dark ages. Their contribution may have been disproportionately large. While the first small galaxies provided the foundation for reionization, it's possible that the globular clusters forming within them provided the critical, concentrated bursts of power that made the process efficient enough to occur on a cosmically rapid timescale. They were the catalysts dramatically accelerating the clearing of the cosmic fog. This idea gains further support from the fact that the epoch of globular cluster formation, as dated by the oldest clusters we see today, aligns perfectly with the timeline of reionization. They were being born in vast numbers right when the universe needed them most. The legacy of this ancient role might even be written into the clusters we see today. The process of blowing away the leftover gas from a cluster after its first burst of star formation is a key part of the multiple population puzzle we discussed earlier. The incredible radiation pressure needed to clear out that gas, allowing a second generation to form from the polluted remains, is a smaller-scale echo of the same process that would have cleared pathways for UV photons on an intergalactic scale. By studying the dynamics of gas in young clusters in nearby galaxies, we can build models of how efficiently these cosmic engines could have contributed to reionization. The story of the universe's Great Awakening is therefore not just a tale of the first galaxies, but also a tale of the first and most brilliant stellar cities within them, whose collective light helped sculpt the transparent cosmos we observe today. Yet another layer of this chemical mystery manifests in a stunning visual pattern across the night sky, one that has had astronomers debating for decades. When you plot the stars of a globular cluster on a color magnitude diagram, the horizontal branch should, in theory, be a straightforward feature. It's the phase where stars, having left the red giant branch, are now stably burning helium in their cores. For a long time, the primary factor thought to dictate a star's position on this horizontal branch was its overall metal content, or metallicity. The logic was simple. Stars with fewer metals are more transparent, allowing heat to escape more easily, which results in a hotter, bluer appearance. Therefore, a metal-poor cluster should have a horizontal branch populated mostly with hot, blue stars, while a metal-rich cluster should have a horizontal branch dominated by cooler, red stars. This single-parameter rule seemed elegant and held true for many clusters. But as astronomers surveyed the galactic halo, they found glaring, baffling exceptions that shattered this simple picture. This is the essence of the notorious second parameter problem. Consider two clusters located at roughly the same distance from the galactic center, meaning they experience similar tidal forces and environmental conditions. According to the single parameter rule, if these two clusters have the same metallicity, their horizontal branches should look identical. Yet, when we compare a cluster like Messier 3 with one like Messier 13, which have nearly identical metal content, the difference is dramatic. Messier 3 boasts a horizontal branch that is long and well populated across its entire length, with a significant number of stars on the blue end. Messier 13, however, displays a horizontal branch that is almost exclusively blue, a brilliant but strangely lopsided arc of hot stars with very few red ones remaining. Something else beyond metallicity is clearly at work sculpting the fate of these stars. This mysterious second parameter is the key to understanding why clusters of the same chemical composition can have such radically different evolutionary pathways. The hunt for this second parameter has become a major endeavor in stellar astrophysics, with several compelling candidates emerging. The most prominent suspect is the very element we've seen causing so much trouble, helium. As we've discovered, second-generation stars in clusters are often enriched with helium. A star born with a higher helium abundance has a fundamentally different internal structure. Its core is denser and hotter, which leads to a more vigorous helium-burning phase. When such a star reaches the horizontal branch, its enhanced helium abundance causes it to land on the blue side. Therefore, a cluster with a significant population of helium-rich second-generation stars will naturally have a bluer horizontal branch. The proportion of these stars within a cluster could be the hidden variable that explains the morphological differences we see between otherwise chemically similar clusters. Another strong candidate is the cluster's age. While all globular clusters are ancient, they are not all precisely the same age. Differences of even 1 or 2 billion years can have a profound effect. An older cluster has had more time for dynamical evolution to occur. Through the constant gravitational interactions in a dense core, the cluster undergoes a process called mass segregation, where lighter stars are pushed to the outskirts and heavier stars sink to the center. Since the stars that evolve onto the horizontal branch are of a specific mass range, this dynamical sorting can alter the population of stars available to enter that phase. An older cluster may have a different distribution of stellar masses in its core compared to a slightly younger one, which could influence the final appearance of its horizontal branch. The cluster's age, therefore, might not just be a number in a catalogue, it could be an active sculptor of its present-day appearance. The true answer likely involves a complex interplay of these and other factors. The central concentration of a cluster plays a role. A denser core with more frequent stellar encounters could lead to a higher rate of mass transfer in binary systems or even direct collisions, creating unusual blue stragglers and affecting the horizontal branch population. Even the precise orbital path of the cluster around the galaxy might be a factor, as clusters on more radial orbits experience stronger tidal shocks that could potentially strip away the outer envelopes of red giant stars before they fully evolve, nudging them toward the blue end of the branch. The second parameter problem is therefore not a puzzle with a single solution, but rather a gateway into appreciating the rich and varied life histories of these stellar systems. It reminds us that a globular cluster is not defined by a single characteristic, but by the intricate combination of its initial conditions and the billions of years of dynamic evolution that have followed, with each cluster writing its own unique story in the arrangement of its stars. Yet the most profound clues to the existence of these dark matter clumps may not come from the destruction of a cluster, but from the subtle, silent influence they exert on the ones that survive. This brings us to a frontier of astronomy where the ancient paths of globular clusters become our most sensitive instruments for mapping the invisible. The concept is deceptively simple. If our galaxy's halo is filled with a swarm of dark matter subhalos, as the leading cosmological model predicts, then their gravitational pull should leave a mark on anything that passes nearby. A globular cluster, with its vast mass and well-defined orbit, is a perfect test particle. As it journeys through the halo over billions of years, its path should be subtly perturbed, its orbit gently nudged and altered by close encounters with these unseen concentrations of mass. The challenge and the opportunity is to detect that faint gravitational whisper against the background hum of the galaxy. The method for this detection relies on a combination of exquisite measurement and sophisticated simulation. First, astronomers must chart the current trajectory of a globular cluster with incredible precision. This involves using observatories like the European Space Agency's Gaia mission, which is mapping the positions and motions of over 1 billion stars in the Milky Way. For nearby globular clusters, Gaia can measure the proper motion, the tiny, actual movement across our line of sight of individual stars within the cluster's outskirts. By averaging these motions, scientists can reconstruct the cluster's precise velocity vector, its direction and speed through space. Combine this with its known distance, and you have a very accurate snapshot of its current orbit. But that is only half the story. To see the perturbations, you need to know what the orbit should have been in the absence of any disturbances. This requires running complex computer models of the Milky Way's gravitational field, treating it as a smooth, symmetric potential, and then integrating the cluster's orbit backwards in time for billions of years. If the actual path of the cluster, traced back using its current velocity, deviates significantly from the path predicted by the smooth model, the discrepancy is the smoking gun. It is the cumulative effect of all the gravitational kicks the cluster has received from dark matter substructure throughout its long history. It's as if you were trying to reconstruct the route of a ship that crossed the ocean long ago. If you only knew its point of departure and its final landing point, you might assume it took a straight line. But if you could examine its detailed logbook and find small but consistent deviations from that straight line, you could infer the presence of unseen ocean currents that pushed it off course. The expected signatures of these encounters are subtle but distinct. A close pass by a massive dark subhalo could impart a noticeable kick, leaving a kink in the cluster's tidal tail or causing a group of extra-tidal stars to lag behind or run ahead of the mainstream. On a broader scale, the very shape of a cluster's orbit around the galaxy could be altered over time. Instead of a simple, smooth ellipse, the orbit might show signs of precession or a change in its orientation that cannot be explained by the gravitational pull of the Milky Way's large-scale components alone. These are the fingerprints we are searching for. The goal is to move from simply knowing that dark matter exists to understanding its granularity, its distribution in clumps and streams throughout the galactic halo. This search is more than an academic exercise. It is a critical test of the cold dark matter paradigm, which is the foundation of our modern understanding of cosmic structure formation. This model predicts that the Milky Way's halo should be teeming with thousands of small dark matter subhalos. Yet, when we look around with optical telescopes, we don't see nearly that many small, companion dwarf galaxies, which are thought to be the visible tracers of the largest of these subhalos. This is known as the missing satellites problem. Are the smaller subhalos truly there but simply too dark to see, or is our theory flawed? By using globular clusters as probes, we can effectively weigh these dark clumps directly through their gravity, bypassing the need for any visible light. If their orbits show the statistical signs of being perturbed by a large population of subhalos, it would provide powerful, indirect confirmation that the dark matter halo is indeed as lumpy as the theory suggests. If, however, the orbits of globular clusters are perfectly consistent with a smooth halo, it would force a radical rethink of the nature of dark matter itself, potentially pointing toward alternative models where dark matter is more evenly distributed or interacts in ways we don't yet understand. The potential of this technique is immense, turning each globular cluster into a natural gravitational sensor. As we continue to gather more precise data from Gaia and other missions, the subtle dance of these ancient star cities will reveal the hidden architecture of our galaxy's dark matter scaffold, allowing us to see, for the first time, the fine-grained structure of the universe's most mysterious component. But if the ghostly streams of disrupted clusters offer a glimpse of a future fate, then the case of Palomar 5 presents a picture of this cosmic dissolution in its most exquisite and scientifically valuable form. Located in the constellation Serpens, Palomar 5 is not a glorious sight through a backyard telescope. It is a faint, wispy smudge of light, one of the least concentrated globular clusters known in the Milky Way. Its sparseness is not a sign of youth, but rather the hallmark of a system in its final death throes. What makes Palomar 5 truly extraordinary, however, is not the cluster itself, but what has been pulled from it. Stretching across an incredible 20 degrees of the sky, 40 times the width of a full moon, are two vast, graceful rivers of stars flowing ahead of and behind the cluster in its orbit. These are the most spectacular and pristine tidal tails ever discovered, a direct and stunning visualization of the Milky Way's gravitational power to unravel a stellar system. The existence of these tails was only revealed through the power of large-scale digital sky surveys. The stars that make them up are individually far too faint to see, but by meticulously mapping the positions and motions of millions of points of light, astronomers can filter out the foreground stars of the Milky Way and uncover these coherent structures. The resulting image is breathtaking. Palomar 5 sits at the center, a dying heart, with two long, thin streams of its former stars stretching out like the wings of a celestial butterfly. The sheer length of these tails tells a clear story. This disruption has not been a recent, violent event. Instead, it has been a slow, relentless process occurring over many orbits, with the galactic tide gently plucking stars from the cluster's loosely bound outer regions each time it swings close to the galactic center. The process is so advanced that the tails now contain far more stars than the cluster itself. Palomar 5 has already mostly been converted from a sphere into a stream. This transformation, while fatal for the cluster, has created a gift for astronomers. The Palomar 5 stream is an almost perfect laboratory for studying the gravitational field of our galaxy. Because the stars in the stream all originated from the same parent cluster and are following very similar orbits, they act as a series of test particles, tracing out the gravitational contours of the Milky Way's dark matter halo. The stream is incredibly narrow and smooth, which indicates that it has been orbiting in a relatively quiet, symmetric gravitational field. But it is the subtle imperfections in this smoothness that hold the greatest promise. According to the leading cosmological model, the halo of our galaxy should be filled with hundreds of smaller clumps of dark matter, the invisible scaffolding left over from the formation of the cosmic web. If one of these dark matter subhalos were to pass near the stream, its gravity would punch a hole in the stellar flow, creating a visible gap or a kink. Hunting for these gaps is like looking for the footprints of an invisible giant. A recent study of the Palomar 5 stream using data from the Gaia spacecraft and the Samuel Oskin telescope did, in fact, uncover a series of small gaps and wiggles along its length. While more analysis is needed to confirm the cause, these irregularities are exactly the kind of signature expected from encounters with dark matter substructure. By carefully measuring the size and spacing of these gaps, astronomers can effectively weigh the dark matter clumps that cause them, providing the first detailed census of the small-scale structure of the dark matter halo. This turns the dying cluster into one of the most sensitive detectors for dark matter we possess, its stretched-out form recording every gravitational whisper it has encountered over billions of years. Beyond mapping dark matter, the Palomar 5 system offers a clear window into the final stages of a globular cluster's life. Its very existence helps explain a long-standing mystery, why we see so few clusters with very low central densities. The answer may be that they are transient. A cluster like Palomar 5, born with a relatively loose structure, is exquisitely vulnerable to tidal forces. It represents a short-lived phase in the life cycle of these objects, a phase that ends not with a bang, but with a slow, graceful unraveling into a stream that will eventually disperse completely into the galactic halo. By studying its current state, we can calibrate our models of cluster evolution, understanding exactly how quickly the tidal stripping process occurs. The magnificent tails of Palomar 5 are therefore more than just a beautiful cosmic accident. They are a detailed chronicle of gravitational interaction, a natural experiment that allows us to probe the forces that shape our galaxy, both seen and unseen. While we have been exploring the grand gravitational and stellar dramas within globular clusters, there is another, more subtle light being emitted from these ancient systems, a light that speaks not of collisions or black holes but of complex chemistry. When astronomers point infrared telescopes toward these clusters, they are looking for the gentle warmth of cool stars and the faint glow of circumstellar dust. But in the spectra of some clusters, they have found something entirely unexpected, a set of peculiar, bright emission bands at specific infrared wavelengths. These are not the clean, sharp lines of atomic gases. They are broad, fuzzy humps and bumps that have been detected in the nebulae of our own galaxy, where they are known as the unidentified infrared emission features. For decades, the prime suspects for producing these features have been complex organic molecules called polycyclic aromatic hydrocarbons, or PAH. Think of them as microscopic flakes of soot, flat molecules made of rings of carbon atoms with hydrogen attached to their edges, much like tiny fragments of graphite or the char on a piece of toast. When these molecules are illuminated by ultraviolet light, they vibrate and rotate, emitting a distinctive pattern of infrared radiation, a chemical fingerprint. The profound mystery is not the existence of PAHs themselves, but their presence within the ancient metal-poor environment of a globular cluster. In the disk of the Milky Way, PAHs are commonplace. They are found in clouds of gas and dust, in the atmospheres of carbon-rich stars, and in planetary nebulae. Their formation is well understood. They are built up from smaller carbon compounds in the dense, dusty envelopes of aging stars and are then blown into space to become part of the interstellar medium. This process relies on a ready supply of carbon and other elements that are the products of stellar nucleosynthesis. But a classic globular cluster is the last place you would expect to find such a rich chemical soup. These are among the most pristine environments known, with stellar populations that are notoriously poor in metals, the very elements needed to build complex molecules. The gas that formed the cluster's stars was virtually pure hydrogen and helium. Furthermore, the fierce radiation from the cluster's many hot, blue stars should be incredibly effective at destroying these delicate organic molecules. Ultraviolet photons can easily break the bonds in PAHs, a process called photodissociation. So, the detection of these emission features presents a double paradox. How did the raw materials to form PAHs ever come to exist in such a chemically simple environment? And how have these fragile molecules managed to survive for billions of years under an intense ultraviolet bath? Several intriguing theories have been proposed to solve this chemical conundrum, each with dramatic implications. One possibility is that the PAHs are not ancient at all, but are relatively recent arrivals, manufactured by the cluster's own stellar population in a late burst of activity. While the massive, short-lived stars that could produce large amounts of carbon died long ago, there is another class of star that takes much longer to evolve, intermediate mass stars similar to our Sun. After billions of years on the main sequence, these stars evolve into asymptotic giant branch stars or AGB stars. In this final, luminous phase, they become prolific factories of carbon, dredging it up from their cores and expelling it into space in powerful stellar winds. It is conceivable that over the last few billion years, a significant population of these AGB stars within a cluster could have enriched a small reservoir of gas with carbon, providing the feedstock for PAH formation. However, this theory faces the challenge of the cluster's destructive environment. The material shed by these stars would be rapidly diluted and exposed to the harsh cluster radiation field, making it difficult for the slow, delicate process of molecule building to occur. An even more fascinating possibility is that the PAHs are not being produced in situ at all, but are interstellar interlopers. Globular clusters orbit the galaxy, and on their long journeys, they occasionally plow through clouds of gas and dust in the Milky Way's disk or halo. It is possible that during such a passage, a cluster could accrete a small amount of material from the outside, material that is already rich in these complex molecules. The cluster's gravity could capture this dust, and though most of it would be quickly evaporated by starlight, some might survive in shielded pockets long enough for us to detect its infrared signature. This would make the PAHs not native to the cluster but a temporary contamination, a cosmic dusting acquired on its travels. If this is the case, then detecting these features could actually tell us something about the cluster's orbital history and its interactions with the galactic environment. Perhaps the most revolutionary idea is that the features are real and ancient, but that our identification of the culprit is incorrect. What if the emission bands are not from PHs at all, but from some other form of carbon-based material that is more robust? Scientists have proposed alternatives like hydrogenated amorphous carbon grains or even nanodiamonds, tiny carbon structures that could form under the extreme conditions of a stellar atmosphere or a supernova shockwave and would be far more resistant to destruction by ultraviolet radiation. The presence of such durable materials would suggest that the chemical evolution within globular clusters is more complex than we thought, capable of producing a wider variety of solid matter even in a low-metal environment. Unraveling this mystery requires more than just detecting the features. It requires studying their exact profile. The relative strengths of the different emission bands can act as a diagnostic tool, revealing the size, charge, and structure of the emitting particles. By obtaining high-resolution infrared spectra from telescopes like the James Webb Space Telescope, astronomers can analyze these fingerprints in exquisite detail, potentially distinguishing between PHs and other candidate materials. The implications of solving this mystery extend far beyond the clusters themselves. If complex organic molecules like PHs can indeed form and persist in these ancient, hostile environments, it profoundly expands the range of places in the universe where the building blocks of life could be present. It suggests that the chemical pathways to complexity are more universal and resilient than we imagined, able to operate even in conditions that were once thought to be far too primitive and harsh. The faint, unidentified infrared glow from a globular cluster is therefore a message in a bottle, a signal that challenges our understanding of chemical enrichment and the durability of molecules across cosmic time. It transforms these stellar cities from simple collections of stars into potential repositories of complex chemistry, adding yet another layer of profound mystery to their already enigmatic nature. If the quiet unraveling of a cluster like Palomar 5 shows us a slow, graceful end, then the grandest scale of cosmic violence reveals their spectacular beginnings. To understand the true origin story of globular clusters, we must zoom out from individual galaxies and witness the most colossal events in the universe, galaxy mergers. When two giant spiral galaxies, each containing hundreds of billions of stars, are drawn together by gravity, their collision is not a simple crash. It is a slow, majestic dance of destruction and rebirth that unfolds over hundreds of millions of years. As the galaxies intertwine, their structures are completely torn apart, spiral arms are shredded, and immense tidal forces pull vast streams of stars and gas into long, graceful arcs. Within this cosmic chaos, something extraordinary happens. The conditions become perfect for birthing a new generation of globular clusters on an epic scale. The key ingredient is pressure. The collision of two galaxies compresses their massive reservoirs of interstellar gas to an extreme degree. Giant molecular clouds, which might normally form stars at a leisurely pace, are suddenly squeezed by shockwaves traveling through the colliding system. This incredible pressure triggers a ferocious burst of star formation, a phenomenon so intense it is called a starburst. But unlike the isolated star formation in a quiet spiral arm, this starburst occurs on a galactic scale, and it doesn't just produce individual stars. It favors the formation of massive, dense, gravitationally bound star clusters, the very definition of globular clusters. It's as if the violence of the merger shakes the entire system, causing star formation to occur not in a trickle, but in a sudden downpour of colossal stellar cities. The most compelling evidence for this link comes from observing galaxies that are currently undergoing mergers. The famous antennae galaxies, a pair of colliding spirals, provide a stunning real-time laboratory. Hubble Space Telescope images reveal not just the chaotic swirl of the galaxies themselves, but hundreds of brilliant, young, blue point-like objects scattered throughout the interaction zone. These are not individual stars, they are infant globular clusters, some containing millions of stars, blazing with the light of their recently ignited suns. Their youth is proven by their intense blue color, indicative of massive, hot, short-lived stars. These clusters are the direct products of the merger, forming right before our eyes from the compressed gas of the galactic collision. This observation powerfully demonstrates that the recipe for creating a globular cluster is not locked in the distant past. It is a process that can be reignited whenever the universe provides the necessary trigger of extreme pressure and turbulence. The fossil record of this violent history is written in the demographics of ancient, quiet galaxies, particularly the giant elliptical galaxies that dominate the centers of galaxy clusters. These smooth, featureless behemoths, unlike their spiral cousins, often possess staggering numbers of globular clusters, thousands or even tens of thousands, orbiting them in a vast spherical halo. Why would one galaxy have so many more than another? The answer appears to be their formation history. The leading theory for the creation of the largest elliptical galaxies is that they are the end products of multiple major mergers. Each merger event doesn't just add stars to the galaxy, it also adds, or more importantly, creates a new population of globular clusters. A spiral galaxy like the Milky Way might have 100 or 200 clusters, relics from its own initial collapse. But when two such galaxies merge, the resulting elliptical galaxy inherits the clusters from both progenitors, plus an entirely new batch forged in the fire of the collision itself. This creates a predictable and testable correlation. The more massive an elliptical galaxy is, and the more violent its past merger history is believed to be, the larger its system of globular clusters tends to be. Furthermore, we can often see two distinct families of clusters orbiting these giants, a red population and a blue population. The blue clusters are typically older and metal-poor, believed to be the original clusters from the progenitor galaxies that were accreted during the merger. The red clusters, richer in metals, are often the ones formed during the merger event from gas that had already been enriched with heavier elements by previous generations of stars. This two-toned halo is a permanent chemical fingerprint of the galaxy's assembly, a layered history book written in starlight. The globular clusters are not merely inhabitants of these galaxies, they are artifacts of their construction, each one a timestamp from a major epoch of growth through violent collision. Their vast numbers in ellipticals are not an anomaly, they are the expected outcome of a history written in mergers, turning these galaxies into cosmic museums displaying the trophies of their most dramatic acquisitions. Just when we think we've mapped every detail of a globular cluster's stellar population, a subtle but systematic anomaly emerges, one that requires us to look not just at what kind of stars are present, but at the precise shade of their light. This brings us to a discovery that seems to defy a fundamental expectation of stellar physics, an effect known as the blue tilt. The premise is rooted in the basic logic of a color magnitude diagram. For a simple, co-eval population of stars, the main sequence should be a clean, narrow band. The most massive, luminous stars are hot and therefore appear blue, while the less massive, fainter stars are cooler and appear red. It's a smooth and predictable gradient. However, when astronomers began studying metal-rich globular clusters, those with a higher abundance of elements heavier than helium, they noticed something peculiar happening at the very top of the main sequence. The very brightest stars, the ones that should be the bluest of all, were not falling exactly where the models predicted. Instead, the entire upper main sequence appeared to be tilted. The brightest stars were consistently shifted ever so slightly toward the blue. This blueward tilt is a subtle effect, but its implications are significant because it challenges the idea of a truly simple stellar population. If all the stars in a cluster are the same age and composition, their positions on the main sequence should be determined solely by their mass. A tilt suggests that an additional factor is at play, subtly altering the color of the most massive stars. One of the leading explanations for this phenomenon involves the complex physics of stellar atmospheres, particularly in stars that are rotating at high speeds. Massive stars are often rapid rotators, spinning so fast that their shape becomes oblate, bulging at the equator. This rapid rotation can induce powerful mixing within the star, churning up material from the hot, fusion-powered core and bringing it closer to the surface. This process, coupled with the effect of centrifugal force reducing the effective gravity at the star's equator, can alter the star's atmosphere. These changes can affect how light is emitted from different parts of the star's surface, potentially making the star appear hotter and bluer than a non-rotating star of the same mass and age. In a metal-rich environment where atmospheric opacities are higher, these rotational effects might be amplified, creating the systematic blue tilt we observe. Another compelling hypothesis connects this tilt directly to the mystery of multiple stellar populations. We've already seen that many clusters contain a second generation of stars enriched with helium. Helium is a lighter element than hydrogen, and it makes a star's atmosphere more transparent. For a given mass, a helium-enriched star will have a hotter, more compact core and a hotter surface temperature, causing it to appear bluer. Now imagine that within a metal-rich cluster, the second generation of stars, the ones born from the polluted gas of the first generation, are also systematically more helium-rich. If these helium-rich stars are present, they would not form a separate clump on the diagram. Instead, they would blend into the main sequence, but they would position themselves slightly to the blue side of a standard star of the same mass. If the fraction of these helium-rich stars increases with stellar mass, perhaps because they formed preferentially in the denser, more polluted central regions where more massive stars were also likely to form, then the net effect would be a gradual blueward shift of the entire upper main sequence. The tilt, in this view, is not an atmospheric illusion but a direct chemical fingerprint, a subtle gradient in helium abundance that is written into the very color of the cluster's brightest suns. A third, more dramatic possibility is that the blue tilt is a sign of very tiny age differences. While globular clusters are ancient, the formation of the second generation of stars might not have been an instantaneous event. It could have been drawn out over a period of tens or even a few 100 million years. In cosmic terms, this is still a blink of an eye, but for massive stars with lifespans of only a few million years, it is a significant fraction of their existence. If the star formation within the cluster occurred in 2 or more waves, the most massive stars we see today would all be from the very last wave of star formation, making them ever so slightly younger than the lower mass stars that live far longer. Since a younger star of a given mass is slightly hotter and bluer than an older one, this slight age spread could manifest as a blue tilt at the top of the main sequence. This would mean that the cluster's star-forming era was not a single, frantic burst, but a more protracted process, a final, fading gasp of creation before the cluster's gas supply was permanently exhausted. The blue tilt, therefore, is far more than a minor curiosity in stellar photometry. It is a precise diagnostic tool, a deviation from the ideal that reveals the complex realities of a cluster's formation. By measuring the exact amount and character of the tilt in different clusters, astronomers can test these competing theories. Does the tilt correlate with other indicators of helium enrichment? Is it stronger in clusters with higher central densities where dynamical interactions could influence rotation rates? Each observation helps to constrain the models, turning a slight skew in a graph into a powerful clue about the physical conditions. The rotations, the chemical mixtures, and the timelines that govern the assembly of these stellar cities in their youth. It reminds us that even the most seemingly orderly patterns in nature often contain hidden nuances, and that by studying these subtle imperfections, we can uncover the rich and dynamic stories that standard models alone cannot tell. And now we venture into the realm of the most powerful explosions since the Big Bang itself, where the peculiar dynamics of globular clusters may be orchestrating cosmic fireworks of unimaginable intensity. Gamma-ray bursts are the universe's ultimate cosmic detonations, fleeting blasts of high-energy radiation that can, for a few seconds, outshine every other source of gamma rays in the cosmos combined. For decades, astronomers have categorized them into two broad families. There are the short-duration bursts lasting less than 2 seconds, which are strongly linked to the merger of two ultra-dense objects like neutron stars. Then there are the long-duration bursts, which can last from several seconds to several minutes, and these have been firmly connected to the cataclysmic deaths of exceptionally massive stars in events known as hypernova. This neat separation has been a cornerstone of high-energy astrophysics. But what if the extreme environment of a globular cluster could blur this clean distinction, creating a hybrid monster that defies simple classification? The key to this potential link lies in the unique social life of a cluster's core. We've already seen how these dense stellar cities are factories for exotic binary systems, particularly pairs of neutron stars. Through countless gravitational encounters, neutron stars are frequently paired up, their orbits tightening over time through the emission of gravitational waves until they are destined to merge. This is the established recipe for a short gamma-ray burst, a brief, brilliant flash. However, in a globular cluster, the story might not end there. Imagine a binary system consisting of two neutron stars spiraling ever closer. But before they can merge, this pair has a close gravitational encounter with a third object, perhaps another neutron star, or even a massive main sequence star. This three-body interaction could dramatically alter the fate of the system. Instead of a clean merger, one of the neutron stars might be ejected, while the other becomes bound to the new, more massive companion. This new partnership could be the progenitor of something far more spectacular. If the companion is a massive star, the neutron star could eventually be engulfed by its partner as the larger star evolves and expands. The neutron star would then spiral inside the massive star's envelope, a process known as a common envelope phase. This inward spiral transfers a tremendous amount of energy, heating the star's outer layers and potentially causing it to shed its hydrogen envelope. What remains is a tight binary consisting of the neutron star and the exposed, helium-rich core of its massive companion, an object known as a Wolf-Rayet star. This helium star is itself destined to explode as a supernova, but here's where the cluster's magic creates a perfect storm. The neutron star, acting as a gravitational anchor, could influence the collapse of the helium star's core. When the core collapses, it might not form a standard supernova. Instead, the presence of the nearby neutron star could help channel the immense energy into narrow, ultra-relativistic jets that punch through the stellar material at nearly the speed of light. The result would be a gamma-ray burst with a dual personality. It would be a long-duration burst because it is associated with the death of a massive star, the traditional hallmark of long jabbies. Yet, its central engine would be fundamentally different. Instead of being powered solely by the collapse of a single massive star into a black hole, the energy would be supercharged by the accretion of material onto the waiting neutron star, or by the rapid formation of a black hole in a system already rich with angular momentum from the binary interaction. This hybrid engine could produce a long gamma-ray burst in a galactic environment where they are otherwise not expected to occur, far away from the young, star-forming regions of galactic disks. A globular cluster, with its ancient stellar population, is the last place you would predict a massive star to die today. But if such a star were created dynamically, through a merger or a mass transfer event that rejuvenated a lower mass star, it could provide the fuel for this exotic explosion. The implications of this speculative connection are profound. If even a small fraction of long gamma-ray bursts originate from globular clusters, it would force a major revision of our models for these colossal events. It would mean that the progenitor of a long Jabi is not always a solitary, massive star born in isolation, but can sometimes be the product of a complex dynamical history, a stellar system sculpted by billions of years of gravitational interactions. Finding evidence for this is the next great challenge. It would involve precisely locating a long gamma-ray burst and tracing its origin back to an ancient globular cluster in a distant galaxy, rather than to a bright blue star-forming arm. While such a detection has yet to be made, the very possibility underscores the transformative power of dense stellar environments. Globular clusters, it seems, are not just repositories of ancient stars. They are cosmic laboratories capable of concocting rare and violent events that challenge our very understanding of stellar life and death. While the brilliant glow of countless stars defines a globular cluster in visible light, a far more intense and focused energy reveals itself in the X-ray part of the spectrum. Here, astronomers have pinpointed some of the most energetic objects in the nearby universe, known as ultraluminous X-ray sources, or ULCs. These are not the faint, widespread X-ray glow from countless stellar remnants. They are incredibly bright, point-like beacons that can outshine an entire galaxy in high-energy light. The sheer power they emit is the source of a major puzzle. To understand why, we need to consider a fundamental limit in astrophysics called the Eddington limit. This is the theoretical maximum brightness an object can achieve when the outward pressure of its own radiation perfectly balances the inward pull of its gravity. If an object tries to shine brighter than this limit, the radiation pressure would be so intense that it would literally blow away the material that is falling onto it, shutting off the very process that powers the light. For a standard stellar mass black hole about 10 times the mass of our Sun, the Eddington limit is well understood. Yet, the ULXs found in globular clusters are screaming past this limit, shining hundreds or even thousands of times brighter than a stellar mass black hole should be able to. This creates a fascinating dilemma. Either our understanding of accretion physics is incomplete, or we are looking at something much more massive. The leading explanation for these ultraluminous beacons points directly toward the long-sought intermediate mass black hole. If a globular cluster managed to form and retain a black hole weighing a few hundred to a few thousand solar masses, its Eddington limit would be correspondingly higher. Material falling onto such an object could, in principle, generate the incredible X-ray luminosity we observe without violating the laws of physics. It would be a scaled-up version of the accretion process we see in stellar mass black holes, but on a far more magnificent and powerful scale. The presence of a ULX in a cluster would therefore be the most compelling indirect evidence yet for one of these elusive middleweight black holes, finally providing a gravitational anchor massive enough to explain the furious energy output. However, nature often has more than one trick up its sleeve. An equally intriguing possibility is that we are witnessing a stellar mass black hole or neutron star behaving in an extraordinary way, a phenomenon known as super-Eddington accretion. Imagine a black hole that is gorging itself on a tremendous feast of gas. If the rate of infall is incredibly high, the resulting radiation might not be able to escape spherically. Instead, it could be funneled out through the poles of the system in narrow, powerful jets, while the inflowing material is channeled in along the equator. In this scenario, the object itself isn't more massive, it's just eating at a rate that defies normal table manners. The intense X-rays we see would be the focused beam of that jet pointing directly at us, making the source appear far brighter than its true total luminosity. This geometric beaming effect could create the illusion of an ultraluminous source from a relatively ordinary compact object, provided it has a voracious and steady supply of fuel. This is where the unique environment of a globular cluster becomes the critical factor. How could a stellar mass black hole possibly maintain such a prodigious diet? The answer lies once again in the crowded social dynamics of the cluster core. A black hole in such a dense environment has a much higher chance of capturing a stellar companion. But not just any companion. The ideal scenario involves a massive, evolved star that has expanded into a red giant. If such a star is in a tight orbit with a black hole, the black hole's gravity can relentlessly pull the star's distended outer layers onto itself at an astonishing rate. This creates a stable, high-mass transfer system capable of sustaining the super-Eddington accretion needed to power a ULX. The cluster, through its constant gravitational interactions, acts as a matchmaker, creating these volatile and energetic partnerships that would be exceedingly rare in the isolation of the galactic disk. The presence of ULXs in globular clusters, therefore, does more than just add another strange object to the list. It places these ancient systems at the forefront of studying extreme accretion physics. Each ULX is a natural laboratory for testing the limits of how matter behaves under the most intense gravitational fields. By studying the flickering and spectral properties of their X-ray emission, astronomers can try to distinguish between the two models. Is the emission steady and isotropic, suggesting a larger black hole, or does it show signs of variability and beaming, pointing to a stellar mass object in overdrive? The answer may not be the same for every ULX. Some clusters might indeed host the definitive intermediate mass black hole, while others showcase the spectacular drama of a stellar mass black hole consuming a giant star. This duality makes every detection a new chapter in the story, a chance to probe the most energetic processes in the universe from within the seemingly tranquil confines of a million ancient stars. Yet the enduring mystery of the second parameter problem demands a deeper investigation into the forces that can so dramatically sculpt the horizontal branch. We've established that metallicity alone cannot explain why two clusters with identical iron content can display such different stellar distributions. The quest to identify this hidden variable takes us into the intricate interplay of a star's internal chemistry and its external environment, revealing a cluster's history written in the color and placement of its helium-burning stars. One of the most powerful candidates is helium abundance. While metallicity refers to elements heavier than helium, the proportion of helium itself is a critical factor. A star born with a higher helium abundance possesses a denser, more compact core. When this star evolves onto the horizontal branch, its hotter core results in a hotter surface temperature, pushing it decisively toward the blue end of the branch. Therefore, a cluster like Messier 13, with its predominantly blue horizontal branch, might not be older than Messier 3. It might simply harbor a much larger population of second-generation stars that were born rich in helium. The horizontal branch morphology becomes a direct map of the cluster's internal chemical diversity, a legacy of its chaotic, multi-generational youth. Another compelling variable is the subtle but significant influence of a cluster's age. While all globular clusters are ancient, a difference of even 1 or 2 billion years can have a profound effect on their stellar demographics. An older cluster has experienced more time for dynamical evolution to occur. Through a process called mass segregation, where heavier stars sink to the core and lighter stars drift to the outskirts over billions of years, the distribution of stellar masses within the cluster changes. Since the stars that evolve onto the horizontal branch fall within a specific mass range, this gradual sorting can alter the available pool of candidates. An older cluster may have a different mix of masses in its central regions compared to a slightly younger counterpart, which could subtly influence the final appearance of its horizontal branch. It's a reminder that age is not just a number on a chart. It is an active participant in the cluster's ongoing dynamical story, quietly shaping the population of stars we observe today. We must also consider the role of the cluster's structural integrity itself, its central concentration. A cluster with an extremely dense core, perhaps one that has undergone core collapse, subjects its stars to a far more chaotic gravitational environment. In such a crowded stellar metropolis, close encounters and binary interactions are not rare events but commonplace occurrences. These interactions can dramatically alter a star's evolution. A close gravitational pass might strip the outer envelope from a red giant star prematurely, forcing it onto the horizontal branch as a hotter, bluer object than it would otherwise have been. Alternatively, the transfer of mass in a binary system can rejuvenate a star, affecting its mass and composition at the critical moment it begins helium fusion. In a highly concentrated cluster, these dynamical effects could act as a secondary sculpting tool, nudging a greater proportion of stars toward the blue side of the horizontal branch, independent of their initial chemical makeup. A more controversial but fascinating candidate is the rotation of the cluster as a whole. Most globular clusters are considered pressure-supported systems, meaning the random motions of their stars hold them up against gravity with little overall rotation. However, some clusters show signs of systemic rotation, a faint spin that is a relic of their formation from a rotating gas cloud. This rotation could create a slightly anisotropic gravitational field within the cluster. The effects might be subtle, but over billions of years, this could influence the orbits of stars and the dynamics of encounters in a way that preferentially affects stars of a certain mass or in certain regions. Furthermore, the individual stars within a rotating cluster might themselves be spinning faster on average, a trait inherited from the angular momentum of the primordial cloud. As we discussed with the blue tilt, rapid stellar rotation can alter a star's atmosphere and temperature, potentially providing another mechanism for shifting its position on the horizontal branch. The true solution to the second parameter problem likely does not lie in a single, universal answer, but in a complex cocktail of these ingredients. The specific history of each cluster, its formation environment, its retention of gas for a second generation, its dynamical encounters, and its orbital path around the galaxy, combines to write a unique recipe that determines the final, beautiful, and often puzzling arrangement of its stars. This enduring mystery reminds us that these ancient systems are individuals, each with a distinct life story encoded in its light. But the influence of these ancient stellar systems extends far beyond their role as tracers of galactic cannibalism. They are now providing crucial evidence for one of the most significant transformations in the life of a galaxy, the metamorphosis of a vibrant spiral into a quiet lenticular. In the grand classification of galaxies, there exists a mysterious hybrid, the S0 or lenticular galaxy. These systems have the flattened disk and prominent bulge of a spiral like our Milky Way, but they lack the spiral arms and, most importantly, the vibrant blue light of ongoing star formation. They are the cosmic equivalent of a retired artist, possessing the structure of their youth but having lost the active creativity that once defined them. For decades, the origin of these quiet, disk-shaped galaxies has been a major puzzle. How does a star-forming spiral galaxy lose its gas and settle into a serene, almost dormant state? The answer appears to be a process as brutal as it is elegant: ram pressure stripping, and the key witnesses to this celestial mugging are the galaxy's own population of globular clusters. The primary suspect in this galactic transformation is the environment of a galaxy cluster. These are the most massive gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies swimming in a superheated atmosphere of plasma known as the intracluster medium. As a spiral galaxy falls into such a dense cluster, it can experience an effect similar to sticking your hand out of a car window at high speed. The galaxy moves through this thin but incredibly hot gas at velocities of thousands of kilometers per second. The resulting ram pressure can be powerful enough to literally blow the galaxy's own cold, star-forming gas right out of its disk. It's a cosmic wind so fierce that it can scour a galaxy clean of its future fuel for stars. The spiral arms, which are density waves triggering star birth, fade away as the raw material is stripped, leaving behind only the older, longer-lived stars in a smooth, featureless disk, the defining characteristic of an S0 galaxy. This is where globular cluster systems become the star witnesses in this case of galactic assault. A spiral galaxy typically possesses two distinct families of globular clusters. The blue clusters are metal-poor, old, and tend to orbit in a more spherical halo, believed to be relics from the galaxy's initial violent collapse. The red clusters are metal-rich, slightly younger, and are concentrated in the galaxy's bulge and disk, thought to have formed during the more settled period of the galaxy's life alongside the disk stars. When a spiral galaxy is stripped of its gas and transformed into an S0, the process affects these two cluster populations in very different ways. The halo of blue clusters, which orbits far from the gas-rich disk, remains largely untouched by the ram pressure. Their distribution stays spherical and extended. The red clusters, however, which are intimately associated with the disk, tell a different story. As the gas is stripped and star formation halts, no new red clusters can form. The existing population is left as a fossilized record of the galaxy's once active disk. Therefore, by studying the globular cluster system of an S0 galaxy, astronomers can read the history of its transformation. If the S0 truly formed from a stripped spiral, it should have a bimodal color distribution, a clear split between the old blue halo clusters and the fossilized red disk clusters, just like a spiral galaxy, but with no young blue stars to indicate recent cluster formation. This is exactly what observations reveal. S0 galaxies in dense clusters show this signature beautifully. Furthermore, the ratio of red to blue clusters can act as a clock. A galaxy that was stripped very recently might still have a significant population of red clusters, while one that was stripped billions of years ago might have lost some of its red clusters to dynamical evolution, subtly changing the ratio. The clusters provide a permanent chemical and dynamical fingerprint that survives long after the gas itself is gone, offering undeniable proof of the galaxy's spiral past. This evidence firmly establishes ram pressure stripping as a primary mechanism for creating the serene, sky S0 galaxies that populate the cores of rich clusters, solving a long-standing mystery of galactic evolution by using the immutable testimony of the oldest stars. Now, let's turn our attention from the violent ends of clusters to a subtle, almost imperceptible motion. A discovery born not from brilliant flashes of light but from the painstaking measurement of tiny movements across the sky. For centuries, astronomers have tracked the proper motions of stars, the slow, gradual drift of stars against the backdrop of more distant galaxies. This is not the star's true velocity through space, but rather the component of its motion that is perpendicular to our line of sight. Measuring these tiny angles, which are often smaller than the apparent size of a coin seen from several miles away, is one of the most challenging tasks in all of astronomy. When scientists began applying this technique to the stars within globular clusters, they expected to see a consistent pattern. Since all the stars in a cluster are bound together by gravity and moving on similar paths around the galaxy, their proper motions should be largely uniform. But early in the 20th century, a puzzling anomaly emerged. There appeared to be a small, systematic difference between the motions of the brighter stars and the fainter ones. This discrepancy was dubbed the K effect, and for a time it presented a genuine mystery. The initial observation was this: when the average proper motion of the cluster's brighter, presumably closer stars was compared to that of its fainter, presumably more distant stars, the two groups didn't quite align. One interpretation was that this indicated the cluster was not a gravitationally bound system at all, but rather a chance alignment of stars at different distances, with the fainter ones actually being farther away and therefore exhibiting a different apparent motion. This would have completely overturned the nature of globular clusters. However, as our understanding of stellar physics and the scale of the universe improved, a much more profound and useful explanation came to light. The K effect was not an error in our concept of clusters. It was a magnificent clue, a key that could unlock one of astronomy's most fundamental measurements, distance. The true cause of the K effect lies in a concept known as the secular or parallactic proper motion. Imagine our solar system moving through space. We are not stationary observers. We are traveling at a significant velocity around the center of the Milky Way. This motion of the sun creates a perspective effect for any object we look at, much like how trees by the side of the road appear to move backwards when you're driving in a car. For a distant object like a globular cluster, which is itself moving, we see a combination of its true motion and this perspective effect caused by our own movement. The crucial insight is that this parallactic motion is not the same for every star in the cluster. It depends on the star's distance from us. The closer a star is to us, the larger its apparent parallactic motion will be. Since the stars in a globular cluster are all at approximately the same vast distance, the difference in parallax between the brightest and faintest stars is minuscule, but it is not zero. The apparent brightness of a star within a cluster is primarily determined by its intrinsic luminosity, not its distance. A bright giant star is genuinely more luminous than a faint dwarf star. However, there is still a subtle spread in distance because the cluster has a physical size. A star on the side of the cluster closest to us is very slightly nearer than a star on the far side. This tiny difference, when combined with our solar motion, produces the observed K effect. The stars on the near side of the cluster will exhibit a slightly different proper motion due to the parallax effect than the stars on the far side. By meticulously measuring this systematic difference across the entire cluster, essentially using the cluster's own diameter as a giant cosmic ruler, astronomers can calculate the cluster's distance with remarkable precision. The K effect, once a confusing discrepancy, was transformed into a powerful geometric tool, a method for measuring distances that is entirely independent of other techniques like variable stars or white dwarf cooling sequences. This understanding also allowed astronomers to refine another critical measurement, the motion of the sun itself. By analyzing the precise pattern of the K effect across many different clusters scattered around the sky, scientists could disentangle the sun's velocity from the intrinsic motions of the clusters. This provided an independent check on the solar apex, the point in the sky toward which the sun is moving. What began as a minor anomaly in the data became a fundamental technique for calibrating the cosmic distance ladder and understanding our own place in the galactic flow. It's a perfect example of how in science, a small, persistent inconsistency can often lead to a much deeper truth, turning a potential problem into a precise instrument for exploring the universe. Contemplate a world where the night sky is not a dark canvas sprinkled with distant points of light, but a permanent, blazing tapestry of stellar neighbors. From the surface of a planet orbiting a star deep within a globular cluster, the heavens would be an awe-inspiring, almost terrifying spectacle. The closest stars would not be light years away, but mere light weeks or even light days distant, appearing as brilliant orbs rivaling the full moon in brightness. Dozens of stars would shine with the intensity of Venus, and thousands more would be easily visible to the naked eye, casting a soft, perpetual twilight and banishing true darkness forever. This is the breathtaking possibility of a habitable world within one of these ancient stellar cities, a concept that pushes our imagination to its limits and forces us to reconsider the very definition of a hospitable environment. The potential advantages for life in such a setting are as profound as the vista is spectacular. One of the most significant benefits is orbital stability on a galactic scale. A planet within a globular cluster is part of a system that has endured for over 10 billion years, tracing a wide, predictable path far from the chaotic and dangerous center of the Milky Way. Unlike stars in the galactic disk, which oscillate up and down through the plane and risk passing through spiral arms dense with supernova-prone young stars, a cluster world would enjoy a relatively serene existence in the quiet galactic halo. This immense longevity provides a stability that is arguably one of the most crucial ingredients for the rise and evolution of complex life, time. Billions of years of unchanging stellar orbits and a benign galactic neighborhood offer a continuity that is rare in our more turbulent cosmic district. Furthermore, the ancient age of the cluster's stars means that any planets orbiting them have had an extraordinarily long period for biological processes to commence and advance. While our solar system is a sprightly 4.5 billion years old, a planet in a globular cluster could have been circling its star for twice that long, providing an almost unimaginable head start for evolution to work its magic. However, this vision of a stable, ancient paradise is challenged by the very same density that creates its stunning skyline. The greatest threat to any potential life in a globular cluster is the constant gravitational meddling from nearby stars. In our own solar system, the orbits of the planets have been stable for eons because the Sun's nearest stellar neighbor is over 4 light-years away, a distance that renders its gravitational influence negligible. But in the core of a cluster, a star's closest neighbor could be 1,000 times nearer. A passing star, even at a distance comparable to our own Oort cloud, could act as a gravitational bull in a cosmic china shop. Its pull could destabilize the delicate architecture of a planetary system, flinging outer planets into the cold depths of interstellar space or sending inner worlds careening into their parent star. It could wrench a formerly habitable planet from its comfortable orbit, either freezing it into an ice ball or broiling it by swinging it too close to its sun. For life to persist, a planet would need to occupy a remarkably resilient orbit, perhaps within a very tight circle around its star, where the parent's gravity dominates overwhelmingly, creating a gravitational fortress against external perturbations. Alternatively, life might have to be incredibly resilient, capable of surviving cataclysmic orbital shifts that would periodically reset the planetary climate. Beyond the danger of gravitational encounters lies the even more immediate threat of radiation. A globular cluster is not just a collection of serene, sun-like stars. It is also home to stellar remnants that are profound sources of high-energy radiation. Neutron stars and white dwarfs in binary systems pumping out X-rays, and the occasional magnetar capable of sterilizing entire planetary systems with a single gamma-ray flare. The sheer number of stars means the background radiation field within a cluster is likely significantly higher than in our galactic neighborhood. A planet would need a robust magnetic field and a thick atmosphere to shield its surface from this persistent bath of energetic particles. The situation becomes even more dire when considering nova and supernova. While the massive stars that end their lives in core collapse supernova died off billions of years ago, the threat from thermonuclear supernova exploding white dwarfs persists. A nearby supernova event would be far more common in a cluster and could deliver a lethal dose of radiation to any world within dozens of light years, effectively sterilizing it in an instant. For a biosphere to survive, it would either need to be extraordinarily radiation resistant or exist around a star that is fortuitously isolated in a quieter, less dense region of the cluster, perhaps in its outer halo. This leads to the most likely haven for life, the cluster's outskirts. While the core is a dynamic and dangerous gravitational maelstrom, the outer regions of a globular cluster offer a more balanced environment. Here, the stellar density is lower, reducing the frequency of disruptive encounters and the intensity of the background radiation field. A star orbiting in this halo would still enjoy the long-term galactic stability of the cluster, but its planetary system could evolve with a degree of isolation reminiscent of our own solar system. The night sky would still be spectacular, filled with the soft glow of the cluster's core, but the immediate neighborhood would be calm enough for stable planetary orbits to persist for billions of years. In this scenario, the greatest challenge might not be survival, but the development of advanced civilization and astronomy. The permanent glow from countless nearby stars would make it incredibly difficult to see the universe beyond the cluster. The concepts of an expanding universe, distant galaxies, and the cosmic microwave background might remain forever unknown to such a civilization, their entire reality bounded by the walls of their stellar city. Their cosmos would be their cluster, a glittering island in a sea of darkness they could never perceive, a profound and humbling thought that reminds us how our own perspective is shaped by the unique, quiet corner of the galaxy we call home. Yet the echoes of these violent encounters stretch far beyond the confines of their home clusters, sending ripples across the very fabric of spacetime. For decades, the study of globular clusters was confined to the narrow band of light our eyes can see, but a revolutionary new window onto the universe opened in 2015 with the first direct detection of gravitational waves. These ripples, predicted by Einstein a century earlier, are generated by the most extreme cosmic events, the inspiral and merger of incredibly dense objects like black holes and neutron stars. As the data from observatories like LIGO and Virgo accumulated, a pressing question emerged. Where in the universe are these binary pairs forming, and how do they get close enough to merge within the age of the universe? The answer, it turns out, may be happening in plain sight within the ancient stellar cities we've been exploring. Globular clusters have emerged as prime suspect factories for these cosmic collisions. The challenge is one of timing. In the relatively empty galactic field where our Sun resides, two stars born as a binary pair face a difficult path to becoming a merging black hole or neutron star system. The more massive star explodes first, often imparting a powerful kick to its remnant from the asymmetric supernova. This kick can easily disrupt the binary, sending the newly formed black hole or neutron star flying off on its own. Even if the binary survives the first explosion, the second supernova carries the same risk. For the system to remain bound and then spiral inward over billions of years through the emission of gravitational waves is a delicate and seemingly rare process. Yet, the merger rate inferred from LIGO and Virgo observations suggests these events are surprisingly common. There must be an environment that dramatically increases the odds, a place where binaries are not just born but made. This is precisely the specialty of a globular cluster's dense core. The chaotic gravitational environment acts as a relentless matchmaker. A solitary black hole drifting through the core can have a close encounter with a binary star system. Through a complex gravitational dance, the lightest member of the trio can be ejected, leaving the black hole bound to the remaining star in a new, energetic partnership. This process, known as dynamical exchange, is incredibly efficient at creating binary systems containing compact remnants. The cluster essentially forces relationships that would never form in isolation. But the story doesn't end there. Once formed, these exotic binaries are subject to further encounters. A passing star can interact with the binary, transferring energy in a way that shrinks the binary's orbit, hurling it closer together. This process, called hardening, can drastically reduce the time it takes for the two dense objects to spiral together and merge through gravitational wave emission. A merger that might take longer than the age of the universe to occur in the galactic field could be accelerated to just a few billion years within the gravitational pressure cooker of a cluster core. The type of mergers produced might even carry a distinct signature pointing to their origin. Dynamically formed binaries are essentially random pairings. There is no reason why the two black holes should have similar masses. They are simply the products of whatever stars happen to collide or exchange partners. This could lead to a population of mergers with high mass asymmetry, where one black hole is significantly larger than the other. Furthermore, The spins of the black holes in a dynamically formed binary are also expected to be randomly oriented relative to each other, unlike in a binary born from two stars that evolved quietly together. By carefully measuring the masses and spins of the merging black holes from their gravitational wave signals, scientists hope to distinguish between mergers born in the isolated galactic field and those forged in the turbulent social halls of globular clusters. Each gravitational wave event is therefore not just a detection. It is a data point that helps us trace the life story of the objects involved, from their birth in stellar fire to their final, violent union. But this delicate balance between what we see and what we infer through gravity can sometimes be thrown into question, revealing hidden aspects of a cluster's population. While the majority of globular clusters present a mass-to-light ratio that aligns perfectly with a collection of normal stars, a few notable exceptions stand out, displaying values that are subtly but significantly higher than expected. This anomaly is a quiet clue, a hint that there might be more to these stellar cities than meets the eye or the telescope. The mass-to-light ratio is a deceptively simple concept. It's the total mass of a system divided by its total luminosity. For a group of stars like our Sun, this number is roughly 1, measured in units of solar mass and solar luminosity. In a globular cluster, which is made up of a mix of stars of different masses and brightnesses, astronomers can calculate what the ratio should be based on our sophisticated models of stellar evolution. For most clusters, the observed stellar motions confirm this prediction, indicating that the gravity we measure is indeed produced by the starlight we see. However, when the calculated mass derived from the speeds of orbiting stars is significantly greater than the mass accounted for by all the visible stars, we are faced with an intriguing puzzle. This discrepancy points to the presence of unseen mass or dark matter, but as we've already discovered, globular clusters are famously lacking in this mysterious substance. So what, then, is causing the extra gravity in these anomalous cases? The leading explanation takes us into the cluster's graveyard. A globular cluster is not just a collection of living stars, it is also a vast repository of stellar corpses. Over its 13 billion-year lifetime, countless stars have lived out their lives and died. The most massive ones ended in supernova explosions, leaving behind neutron stars and black holes. The vast majority of Sun-like stars have gently shed their outer layers to become white dwarfs. These stellar remnants, especially the neutron stars and black holes, possess tremendous mass but emit little to no light. They are the invisible anchors of the cluster. Whether these dark remnants remain within the cluster or are ejected is a key factor that determines its mass-to-light ratio. Through the process of dynamical friction, the heaviest remnants tend to sink toward the cluster's core over time. If a cluster is particularly good at retaining this population of neutron stars and black holes, their collective mass would contribute significantly to the overall gravity without adding to the luminosity. This would inflate the mass-to-light ratio, creating the observed anomaly. The ability of a cluster to hold onto these heavy objects depends on its own gravitational strength and its orbital path around the galaxy. A massive, tightly bound cluster on a wide, gentle orbit is far less likely to have its remnants stripped away by galactic tides than a smaller, looser cluster on a punishing path that brings it close to the galactic center. Therefore, an anomalous mass-to-light ratio can be a fingerprint of a cluster's dynamical history, revealing its success in holding onto the dark products of its stellar generations. An alternative and equally fascinating possibility is that the anomaly stems from the very beginning of the cluster's life. Perhaps these clusters were born with an unusual initial mass function, the distribution of stellar masses at their birth. The standard initial mass function favors the formation of many low-mass stars for every high-mass star. But what if, in the extreme pressure and density of a particular star-forming cloud in the early universe, the process was skewed? Maybe the cloud fragmented in a way that produced a higher proportion of low-mass stars than we typically expect. Since low-mass stars are very faint for their mass, a red dwarf might have half the mass of the Sun, but less than a tenth of its brightness. A cluster dominated by them would have a high mass-to-light ratio. It would be heavy but dim. This would mean the anomaly is not about what the cluster has lost over time, but about the unique recipe it was born with, a fossilized imprint from its formation that has persisted for billions of years. These anomalous ratios, therefore, act as diagnostic tools, forcing us to look deeper into both the life cycle and the birth conditions of these ancient systems to understand the full story of their mass. This grand, gradual dispersal of globular clusters is not a meaningless fade into darkness. It is a vital, ongoing contribution to the very architecture of the galaxy itself. Each star that is stripped away by the galactic tide or flung out by a gravitational encounter becomes a solitary traveler, but it does not journey into nothingness. Instead, it joins a vast, diffuse population known as the galactic stellar halo, a spherical cloud of ancient stars that envelops the bright disk of the Milky Way. For a long time, the origin of this halo was a mystery. Were these stars the first inhabitants of the galaxy, forming in a rapid, monolithic collapse? Or were they acquired over time like pieces of a cosmic puzzle? The answer, it turns out, is written in the motions and chemistries of these halo stars, and it points directly to the dismantling of globular clusters as a primary source. This idea is central to the theory of hierarchical galaxy formation, which suggests that large galaxies like our own were not born in their present form. Instead, they were assembled over billions of years through the accretion and consumption of smaller building blocks. The first structures to form in the early universe were small protogalactic fragments and dwarf galaxies. As these smaller systems were drawn in by gravity, they were torn apart, their stars scattered into the growing halo of the dominant galaxy. Globular clusters fit into this picture perfectly. Many of them are just as ancient as the oldest halo stars, and they possess the same pristine, metal-poor chemical composition. This makes them ideal candidates for being the surviving remnants of those first building blocks. Some clusters may have formed within those early dwarf galaxies, while others might have been the central, densest kernels of the fragments themselves. The process is a form of cosmic archaeology. By studying the properties of individual stars in the halo, astronomers can often trace them back to a common origin. For instance, stars that share a unique orbital path and a specific chemical fingerprint, like an unusual ratio of certain elements, are likely the dispersed remnants of a single globular cluster or a small galaxy that was digested long ago. The spectacular tidal streams we see, like those from Palomar 5, are the most vivid examples of this process happening in real time. These streams are the direct precursors to the stellar halo. Given enough time, the stars in the stream will drift apart, their shared motion gradually diluted until they blend seamlessly into the anonymous background of the halo. The stream is a snapshot of a cluster in its death throes, a temporary phase before its stars are fully donated to the galaxy's reservoir. This contribution is not insignificant. While the total number of stars in the halo is small compared to the galactic disk, its sheer volume makes it a crucial component of the galaxy's mass and structure. The ancient, metal-poor stars that globular clusters contribute are like living fossils, preserving a record of the conditions in the early universe. Their orbits, which are often highly elongated and tilted relative to the disk, are a frozen memory of the chaotic merger events that built the galaxy. By mapping the orbits and chemistries of these stars, we can effectively rewind the clock, piecing together the sequence of acquisitions that formed the Milky Way as we know it today. The quiet, relentless dissolution of globular clusters is therefore not an end, but a transformation. They are the primary agents responsible for seeding the galactic halo with its oldest stars, acting as the delivery system for the raw materials of galactic construction. Their gradual decay is the mechanism by which the galaxy grows from the outside in, incorporating the legacy of its smaller neighbors to build a vast, structured halo that tells the story of its own assembly. And now we come to what might seem like a simple census problem, but one that points to a dramatic reshuffling of a cluster's population over billions of years. If you were to count all the stars in a globular cluster, you would naturally expect to find a vast number of small, faint red dwarf stars. After all, in our own galactic neighborhood, for every star like our Sun, there are dozens of these diminutive, long-lived red dwarfs. They are the most common type of star in the universe, so when astronomers calculate the theoretical population of a globular cluster based on our standard understanding of star formation, the models predict that these low-mass stars should dominate, far outnumbering their brighter, more massive siblings. Yet when the tallies are made, particularly in the outer regions of some clusters, the numbers don't add up. There is a curious and significant deficit of these faint red stars. It's as if someone has been systematically removing the smallest citizens from the stellar city, leaving behind a population that is strangely skewed toward the brighter, heavier stars. The primary suspect in this missing persons case is a relentless, gravity-driven process we've encountered before: dynamical evolution. In the dense core of a cluster, stars are in a constant state of gravitational interaction, like molecules in a hot gas. Through millions of these encounters, a natural sorting occurs. The more massive stars tend to lose kinetic energy and sink toward the center of the cluster's gravitational well, a journey known as mass segregation. Meanwhile, the lighter, low-mass stars tend to gain energy from these interactions, causing them to migrate outward toward the cluster's outskirts. Over billions of years, this creates a clear demographic divide. The core becomes densely packed with heavy stars, stellar remnants, and binary systems, while the halo becomes enriched with lighter stars. However, this outward migration for the low-mass stars comes with a grave risk. The farther a star moves from the protective center of the cluster, the weaker the cluster's gravitational grip becomes. These stars end up on the frontier, most vulnerable to the external pull of the galaxy. This is where the second culprit enters the picture: tidal stripping. As the cluster orbits the Milky Way, the galactic tide constantly tugs at its outer layers. The stars that are most easily plucked away are those on the most loosely bound orbits, precisely the low-mass stars that have been pushed to the outskirts by mass segregation. Each close pass by the galactic center acts like a gravitational sieve, preferentially stripping away the cluster's lightest members. These stars don't vanish, they are gently pulled from the cluster and set adrift in the galactic halo, joining the vast population of lone stars that orbit the galaxy. This combination of internal dynamics and external tides creates a continuous leak of low-mass stars, a slow but steady erosion that, over the cluster's immense lifetime, can account for a significant portion of the observed deficit. The cluster is effectively being skimmed of its faintest citizens, its population gradually becoming more top-heavy as the eons pass. But there is a third, more radical possibility that challenges our fundamental assumptions about star formation in the early universe. What if the missing low-mass stars were never there in the first place? Our models assume that the initial mass function, the distribution of stellar masses at birth, was universal, meaning it was the same 13 billion years ago in a globular cluster as it is today in the Orion Nebula. But what if that's not true? The conditions in the early universe were incredibly different. The gas was pristine, devoid of the heavy elements and dust that help clouds fragment into small clumps. Perhaps in this primordial environment, the process of star formation was biased. Instead of producing a wide spectrum of stars from heavy to light, the collapsing gas clouds in these infant clusters might have favored the formation of more massive stars. In this scenario, the cluster would have been born with a top-heavy initial mass function, inherently lacking in the abundance of red dwarfs we would otherwise expect. Distinguishing between these theories, a slow stripping over time versus a peculiar birth condition, is a major challenge in modern astrophysics. The key lies in studying clusters in different environments. A cluster on a wide, placid orbit far from the galactic center would experience minimal tidal stripping. If such a cluster still shows a deficit of low-mass stars, it would be powerful evidence for a non-universal initial mass function. Conversely, a cluster on a tight, punishing orbit that brings it repeatedly close to the galactic bulge should show a much more severe deficit, pointing to tidal stripping as the dominant mechanism. By comparing clusters across the Milky Way, astronomers are slowly piecing together this puzzle. The mystery of the missing low-mass stars is more than a bookkeeping error. It forces us to question whether the rules of star formation are truly constant across time and space, or if the universe's first stellar cities were built according to a different, more dramatic blueprint altogether. While the space between stars in our galaxy is a near-perfect vacuum, it's not completely empty. It contains a sparse distribution of gas and dust known as the interstellar medium. For a long time, astronomers assumed that within globular clusters, this medium would be virtually non-existent. The reasoning was straightforward and seemed unassailable. In the early, violent life of a cluster, the first generation of massive stars would have lived short lives and died in supernova explosions. The combined fury of these blasts, along with the powerful stellar winds from the most brilliant stars, would have created a relentless gale, a supernova-driven wind powerful enough to sweep any remaining gas clear out of the cluster's gravitational grip. This cleansing event was thought to be permanent, leaving the cluster's stars orbiting in an ancient, pristine void, a region of space scrubbed clean of the raw material needed to form new stars. This was a key part of the puzzle explaining why all the stars in a cluster appeared so ancient. It was therefore a profound surprise when X-ray telescopes, sensitive to the glow of extremely hot gas, detected a faint but unmistakable signal emanating from within several globular clusters. This wasn't the pinpoint radiation of X-ray binaries. It was a diffuse, soft X-ray glow that permeated the central regions. The only thing that could produce such an emission is a thin, hot plasma, a gas heated to temperatures of millions of degrees. This is the intracluster medium, and its very existence presents a major paradox. How could this tenuous gas be present today, over 12 billion years after the cluster's formation, when every known physical process should have expelled it within the first few 100 million years? It's as if you discovered a room that was supposedly sealed shut centuries ago, still filled with the faint, warm breath of its original occupants. The solution to this riddle points toward a continuous injection process, a hidden source that is constantly replenishing the gas almost as quickly as it is lost. The primary suspect in this cosmic refueling operation is the cluster's own stellar population. While the era of supernova from massive stars is long over, the cluster is still teeming with stars in their later evolutionary stages. Specifically, the gentle but persistent winds from asymptotic giant branch stars, or AGB stars, are a prime candidate. These are sun-like stars that have reached the final stages of their lives, having expanded into giant, luminous orbs. In this phase, they shed their outer layers in a slow, dense stellar wind, pumping significant amounts of gas, primarily hydrogen and helium, back into the cluster environment. Imagine millions of leaves falling from ancient trees in a forest, continuously adding a thin layer of organic matter to the forest floor. Similarly, the collective output of thousands of these aging stars could provide a steady trickle of new material. However, this explanation alone is not sufficient. The gas shed by AGB stars is relatively cool and dense. To explain the observed X-ray emission, this gas must be heated to extreme temperatures. This is where other cluster residents come into play. The same intracluster medium is bathed in the intense radiation field from the cluster's hot stars, like blue stragglers and white dwarfs. Furthermore, the high-velocity winds from pulsars and the shockwaves from other stellar interactions could transfer tremendous energy to this gas, heating it to the millions of degrees required to make it glow in X-rays. The intracluster medium we detect is therefore not the pristine gas from the cluster's birth. It is a recycled, second-generation product, a constantly churning mixture of stellar waste products that is heated, energized, and continuously escaping the cluster's weak gravitational pull, only to be partially replaced by the ongoing contributions from its aging stellar citizens. This discovery reveals that a globular cluster is not a static fossil, but a system with a faint, persistent metabolism, still breathing, however faintly, after all this time. But how do we actually measure the distance to something so far away that its individual stars are just a faint smudge of light? This challenge brings us to one of the most elegant and powerful tools in the astronomer's toolkit, a method that relies not on a single star, but on the collective properties of the entire globular cluster system. It hinges on a remarkably consistent feature that emerges when you take a census of these clusters around any given galaxy. If you plot the number of clusters against their brightness, you don't get a random scatter. Instead, you find a smooth, bell-shaped curve with a distinct and predictable peak. The absolute magnitude or true intrinsic brightness of this peak is astonishingly similar from one large galaxy to the next. This universal peak is known as the globular cluster luminosity function, and it functions as one of astronomy's most reliable standard candles. The reason this peak is so consistent lies in the fundamental statistics of how stars are born. When a giant molecular cloud collapses to form a cluster, it doesn't produce stars of just one size. It creates a full spectrum, from brilliant, heavyweight stars to countless faint, lightweight red dwarfs. The total luminosity of the resulting cluster is essentially the sum of all this starlight. While the number of stars in a cluster can vary wildly from tens of thousands to millions, the way those stars are distributed by mass follows a surprisingly predictable pattern known as the initial mass function. This means that for a large sample of clusters, the combined light of the most probable distribution of stars tends to converge around a specific characteristic brightness. It's a bit like the average height of a human population. While individuals vary greatly, the average for a large, healthy group is remarkably stable. For globular clusters, that average peak brightness is equivalent to about 100,000 suns. This statistical reliability transforms the luminosity function into a powerful cosmic yardstick. The process is beautifully straightforward. First, astronomers use nearby galaxies whose distances have been measured by other methods like Cepheid variable stars to carefully calibrate the absolute magnitude of the peak. They determine with high precision exactly how bright that peak should be. Then, when they look at a far more distant galaxy, they simply identify its population of globular clusters, plot their brightness distribution, and find the peak of that curve. The difference between how bright the peak appears from Earth and how bright they know it truly is directly reveals the distance. If the peak appears faint, the galaxy is far away. If it appears relatively bright, the galaxy is closer. This method is particularly powerful because it doesn't rely on measuring a single, potentially anomalous object. It uses the combined signal of dozens or even hundreds of clusters, making the result robust and statistically significant. The impact of this technique on our understanding of the cosmos cannot be overstated. Throughout the 20th century, a fierce debate raged about the true scale of the universe and the nature of mysterious spiral nebulae. Were they small, nearby objects within our own Milky Way, or were they vast island universes comparable to our galaxy but lying at immense distances? The globular cluster luminosity function provided critical evidence in this great debate. When astronomers like Harlow Shapley and others applied this method, they found that the clusters associated with these spirals were far too faint to be nearby. Their calculated distances placed them far beyond the confines of the Milky Way, delivering a decisive blow to the idea that our galaxy was the entire universe and firmly establishing the extragalactic nature of galaxies. This was a monumental step in transforming our cosmic perspective, revealing a universe filled with billions of galaxies, each a colossal city of stars in its own right. Even today, in an era of more precise distance indicators like supernova, the globular cluster luminosity function remains a vital cross-check and an essential rung on the cosmic distance ladder. It is especially valuable for measuring distances to elliptical galaxies and the central galaxies of clusters, where other standard candles might be scarce. Furthermore, subtle deviations from the universal peak can themselves be scientifically illuminating. If the peak brightness for a particular galaxy is significantly different, it might tell us something unique about that galaxy's history. Perhaps it experienced an unusual burst of cluster formation, or it has undergone a dramatic merger that altered its cluster population. So, this method serves a dual purpose. It provides a reliable measure of vast cosmic distances while also offering clues about the individual life story of the galaxy being studied, a testament to the enduring value of these ancient stellar assemblies. And now we turn our attention to a different kind of stellar heartbeat, one that reveals its secrets not through X-rays or gravity, but through the steady rhythm of radio waves. In the crowded cores of globular clusters, amidst the millisecond pulsars that serve as cosmic clocks, astronomers have identified a peculiar subset that seems to defy the norm. These are the so-called red pulsars. The color red here isn't about visible light, it's a descriptor of their radio spectrum. Most pulsars are brightest at lower frequencies, and their emission fades away as you move to higher frequencies. They have what's called a steep spectrum. But these cluster-dwelling red pulsars take this to an extreme. Their radio emission drops off so dramatically with increasing frequency that they appear virtually invisible to telescopes observing at the higher end of the radio band. It's as if their radio voice is a deep bass that fades into a whisper when you try to hear it at a higher pitch. This unusual property makes them particularly challenging to find, yet their discovery is shedding new light on the complex plasma conditions unique to these dense stellar environments. The leading theory to explain this extreme spectral steepness points directly to the environment these pulsars call home. The space between stars in a globular cluster, especially in the core, is not a perfect vacuum. It is permeated by a very tenuous but significant intracluster medium, a hot, ionized gas that we've already seen can glow in X-rays. When the radio waves from a pulsar travel through this plasma, they don't pass through completely unaffected. The waves interact with the free electrons in the gas, a process known as free absorption. Lower frequency radio waves are more susceptible to being absorbed or scattered by this material. For a pulsar embedded in a particularly dense cloud of this intracluster plasma, the lower frequency waves can be significantly diminished, while the higher frequency waves pass through more easily. However, if the pulsar's own intrinsic emission is already very steep, meaning it's naturally much brighter at low frequencies, the combination of this natural tendency and the absorption by the surrounding gas can create the incredibly steep red spectrum we observe. The pulsar isn't necessarily generating more low-frequency light. It's that the environment is selectively filtering out competing signals, making its deep radio voice stand out more prominently against the cosmic background. This explanation is strongly supported by the fact that a significant number of these red pulsars are found in binary systems. A pulsar with a companion star, particularly a main sequence star that is losing mass through a stellar wind, is effectively sitting inside a private bubble of dense plasma. This provides a localized, intense source of material for the free absorption to occur. The radio waves emitted from the magnetic poles of the pulsar have to travel through this shroud of gas before they can escape into the wider cluster and eventually reach our telescopes. This naturally explains why their spectra are so much steeper than those of isolated pulsars. The binary companion acts as a cocoon, tailoring the pulsar's radio signature into this distinct red profile. This makes these systems invaluable probes. By studying the exact shape of their absorbed spectrum, astronomers can essentially measure the density and temperature of the plasma in the binary system itself, offering a rare glimpse into the conditions of mass transfer and stellar winds in these dynamic partnerships. Beyond the local environment of a binary system, the prevalence of red pulsars in clusters also tells us something fundamental about the cluster-wide plasma. The fact that we see these objects at all suggests that the general intracluster medium is dense enough to have a noticeable effect on pulsar emission. This provides independent confirmation of the faint, hot gas that X-ray telescopes have detected. Each red pulsar acts like a tiny lighthouse whose beam is being modified by the fog it travels through. By mapping the locations and spectral properties of these pulsars, scientists can chart the distribution and density of this elusive plasma throughout the cluster, turning the pulsars themselves into distributed sensors for the cluster's atmosphere. The discovery of red pulsars, therefore, bridges the gap between the study of individual stellar corpses and the global properties of the cluster they inhabit, revealing an intricate relationship between the stars and the space that binds them together. But if we are to use these cosmic clocks to test the very laws of physics, we must first ensure they are keeping perfect time, a task that is far more difficult than it sounds. The unwavering tick of a millisecond pulsar is the foundation of its scientific power. To detect the minuscule timing delays caused by gravitational waves or to map the invisible gas within a cluster, we need to know the expected arrival time of each pulse with extraordinary precision, down to a fraction of a microsecond. Achieving this requires a timing solution, a complete mathematical model that accounts for every single factor that could possibly delay the pulse on its journey from the pulsar to our radio telescopes on Earth. For an isolated pulsar in the calm of the galactic field, this is a challenging but manageable task. For a pulsar buried deep within a globular cluster, it becomes a fiendishly complex puzzle, a true test of our understanding of gravity and motion. The first and most straightforward delay comes from pure geometry, the motion of the Earth. As our planet orbits the Sun, the distance a radio wave must travel to reach us changes throughout the year. We can correct for this with incredible accuracy by using a model of the solar system's dynamics, effectively placing our calculations at the solar system's center of mass. But this is just the beginning. If the pulsar is in a binary system, which many in clusters are, we must also model its orbit with extreme precision. The pulse arrival times will rhythmically advance and delay as the pulsar swings toward and away from us in its dance with its companion. This binary motion can be complex, especially if the orbit is eccentric or if the companion is another neutron star, but it is a deterministic problem that can be solved with patience and careful observation. The true complicating factor, the one that transforms this task from a calculation into a puzzler, is the cluster's own gravitational field. A globular cluster is not a point mass, it is a vast, extended collection of matter. The pulsar is not simply orbiting the cluster's center in a smooth, simple ellipse. Instead, it is moving through a complex, lumpy gravitational landscape, its path subtly perturbed by the combined pull of every single star, white dwarf, neutron star, and black hole it passes. This complex gravitational potential introduces an additional, time-varying delay that is unique to pulsars within clusters. As the pulsar moves through regions of slightly stronger or weaker gravity, the flow of time itself changes for it in accordance with Einstein's theory of general relativity. When the pulsar is deeper in the cluster's gravitational well, its clocks, the mechanisms generating its pulses, tick ever so slightly slower relative to our clocks here on Earth. This gravitational time dilation, while tiny, is significant enough to disrupt the timing solution if not accounted for. But how do you model this? You would need to know the exact mass distribution of the entire cluster, the position and mass of every significant object to predict these subtle delays. This is, of course, impossible. Instead, astronomers must use a statistical approach, modeling the cluster as a smooth distribution of mass with an overall density profile. They can then calculate the average gravitational delay the pulsar should experience based on its projected position within the cluster. However, this smooth model misses the granularity of the cluster. The real delay will have small, random fluctuations caused by close encounters with individual stars or dark remnants. These unmodeled effects introduce a low-level noise into the timing residuals, the difference between the observed pulse arrival time and the time predicted by our best model. This timing noise is the signature of the cluster's chaotic heart, a constant reminder that our precise clock is navigating a gravitational obstacle course. The challenge is even greater for pulsars that happen to lie in the cluster's core, where the density and gravitational fluctuations are most extreme. For these pulsars, the timing noise can be so severe that it becomes difficult to even maintain a coherent timing solution over long periods. A single close encounter with a passing star can give the pulsar a tiny gravitational kick, slightly altering its orbital parameters or its spin period in a way that is effectively unpredictable. When this happens, the carefully built timing model breaks down, and astronomers must essentially start over, refitting the data to find a new solution. This limits our ability to use these particular pulsars for the most demanding experiments, like detecting the faint hum of gravitational waves from supermassive black hole binaries in the distant universe, which requires timing stability over decades. The very environment that makes clusters so rich in pulsars also makes it hardest to exploit their full potential as precision instruments. This timing solution puzzler is therefore a fundamental limitation, a price we pay for observing these natural clocks in the most dynamic stellar environments the galaxy has to offer. We have journeyed through 48 of the strangest discoveries about globular clusters, uncovering mysteries from stellar vampires to galactic cannibalism. But perhaps the most thrilling realization is that this story is far from over. In fact, we are standing on the brink of a new golden age of discovery, one powered by a suite of telescopes so advanced they will make our current view of the cosmos seem like a blurry sketch. The next great revelations about these ancient star cities will come from the James Webb Space Telescope and the coming generation of Earth-based extremely large telescopes, instruments designed to push the boundaries of what is observable, to see the unseen and to measure the unmeasurable. The James Webb Space Telescope, with its immense gold-coated mirror and suite of infrared instruments, is already revolutionizing our view. Its greatest gift to globular cluster science is its profound sensitivity to infrared light. For too long, our view into the dense hearts of these clusters has been obscured by interstellar dust, which scatters and absorbs visible light but allows longer wavelength infrared radiation to pass through relatively unimpeded. JWST acts like a cosmic dustbuster, peering straight through these veils to reveal the stellar populations hiding within, but its power goes far beyond simple imaging. JWST spectrographs can dissect the light from individual stars in a cluster's core with a precision previously unimaginable. Imagine being able to point at a single, faint star among tens of thousands, and within hours obtain a detailed chemical fingerprint, measuring not just broad categories like metallicity, but the exact abundances of carbon, nitrogen, oxygen, and sodium. This capability is the key to finally untangling the mystery of multiple populations. We will be able to map the distribution of first and second generation stars across entire clusters, testing whether the helium-enriched stars truly are concentrated in the cores as some theories predict. We might even detect the subtle chemical signatures of stars from a hypothetical third generation, providing a complete chemical movie of the cluster's dramatic early history. While JWST observes from the pristine environment of space, a parallel revolution is brewing on the ground with the construction of the Extremely Large Telescopes, or ELT. These are not merely incremental improvements, they are colossal observatories with mirrors measuring 30 to 40 meters across, gathering more than 10 times the light of today's largest telescopes. Their most immediate impact on globular cluster research will be through sheer resolution. The immense light-gathering power combined with advanced adaptive optics systems will allow these telescopes to resolve individual stars right into the very centers of clusters in galaxies far beyond our own local group. For the first time, we will be able to perform the same detailed stellar census on clusters orbiting galaxies like Andromeda or the Triangulum Galaxy that we currently only can do for Milky Way clusters. This will answer fundamental questions about whether the strange phenomena we see, the multiple populations, the missing red giants, the blue stragglers, are universal or if they depend on the host galaxy's environment and history. The ALTs will also open a new window on dynamics. By taking a series of high-resolution images over just a few years, astronomers will actually be able to see stars moving within distant clusters. They will track their proper motions with enough accuracy to map the gravitational field in the core directly, providing the most definitive test yet for the existence of intermediate mass black holes. If there is a 20,000 solar mass black hole lurking in the heart of a cluster in Andromeda, the stars circling it will reveal their frantic dance to the watchful eyes of an ALT, ending the debate once and for all. Furthermore, these telescopes will be able to obtain spectra of stars so faint they are currently beyond our reach. This will allow us to search for the subtle chemical signatures of spallation, the enhancement of lithium, beryllium, and boron in the atmospheres of second-generation stars, providing direct evidence that the cluster's youth was indeed a maelstrom of cosmic rays and supernova shocks. The synergy between JWST and the ALTs will be particularly powerful. JWST can identify the most interesting and peculiar stars in a cluster with its infrared eyes, and then the ALTs can follow up with ultra-high-resolution spectroscopy to analyze their chemistry in mind-boggling detail. Together, they will act as a universal laboratory for stellar physics, allowing us to study how stars evolve in an environment 1,000 times denser than our own neighborhood. They will watch as binary stars transfer mass, as blue stragglers form from collisions, and as stellar winds from aging giants slowly replenish the intracluster medium. This isn't just about adding more entries to our list of strange discoveries. It is about understanding the fundamental physics that governs the lives of stars in the most extreme social environments the universe has to offer. The data flowing from these new eyes on the sky will not simply provide answers, they will undoubtedly pose new, even deeper questions, ensuring that the enigma of the globular cluster continues to captivate and challenge us for generations to come. After exploring 49 of the universe's most profound stellar puzzles, we arrive at a question that ties all the others together, a mystery that reaches back to the very beginning of structure in the cosmos. Is there a single, universal recipe for building a globular cluster? Or does the incredible diversity we've witnessed from the helium-rich stars of Omega Centauri to the dark matter-free purity of most clusters, and from the ancient relics of the Milky Way to the youthful giants of the Large Magellanic Cloud point to a more complex truth, that these stellar cities can be assembled through multiple distinct pathways? The answer seems to be that there is no one-size-fits-all origin story. Instead, the formation of a globular cluster is a conditional process, a cosmic outcome dictated by the specific and often violent environment in which it is born. Consider the evidence we've gathered. The traditional picture placed their birth exclusively in the intense, high-pressure environment of the early universe, shortly after the first galaxies began to coalesce. In this scenario, the first giant clouds of pristine gas, collapsing under their own gravity within the nascent dark matter halos of dwarf galaxies, fragmented directly into these dense, massive star clusters. This pathway would naturally produce the ancient metal-poor clusters that dominate the halos of galaxies like our own. Their uniformity in age and their lack of a dark matter component are key predictions of this model, suggesting they formed before the universe was heavily polluted with metals and in regions where the extreme density of gas itself was sufficient to trigger their collapse without needing a massive dark matter halo to confine them. But then we have the confounding existence of young massive clusters, like those shining brightly in the Large Magellanic Cloud. These objects are structurally identical to ancient globular clusters, yet they are billions of years younger. Their formation cannot be pinned to the unique conditions of the cosmic dawn. Instead, they were forged in the fire of galactic collisions and close encounters, where the tidal forces of interacting galaxies compressed giant molecular clouds to the point of triggering a furious burst of star formation. This proves that the essential ingredient is not when you form, but how. Any event that can generate the necessary extreme pressure, whether it's the primordial collapse of the universe or a galactic train wreck happening today, can birth a globular cluster. This is a second, independent pathway. Furthermore, the bizarre chemical fingerprints of multiple populations add another layer of complexity. For a cluster to hold onto enough gas to form a second, chemically distinct generation of stars, it must have been incredibly massive from the start, with a gravitational well deep enough to withstand the cleansing fury of the first supernova. This suggests that the clusters showing the strongest chemical anomalies might have formed in the most extreme overdensities of the early universe, perhaps as the very nuclei of the first dwarf galaxies. In contrast, a cluster that formed in a single, quick burst and then expelled all its gas would show a simple stellar population. The diversity in chemical complexity among clusters today is therefore a direct reflection of a diversity in their initial conditions and formation histories. This leads us to a grand unifying yet wonderfully diverse picture. Globular clusters are not a single class of object with a single origin. They are a family whose members share a common architectural principle, a dense, gravitationally bound sphere of stars, but who were built from different blueprints and under different circumstances. Some are true relics from the epoch of first light, formed in the frantic initial collapse of cosmic structure. Others are the products of later, more localized violence within galaxies, like mergers and intense starbursts. And some, like Omega Centauri and M54, are likely the surviving cores of devoured dwarf galaxies, a third pathway where what we call a cluster is actually the fossilized heart of a much larger system. Their collective story is not one of a simple formula, but a testament to the universe's creative versatility, demonstrating that under the right conditions of pressure, density, and dynamics, the cosmos has repeatedly discovered how to build these magnificent, enduring islands of stars. From the very beginning, our journey into these ancient star clusters has been a story of shattered expectations. We set out to explore 50 of their strangest secrets, and at every turn, we found that these glittering orbs are not the simple retirement homes for old stars we once believed them to be. Instead, they are cosmic crucibles where the fundamental rules of physics are tested and sometimes rewritten. We've witnessed the age paradox where stars appear older than the universe itself, forcing us to question the very timeline of the cosmos. We've unraveled the mystery of multiple stellar populations, where stars living side by side have different chemical histories, pointing to a dramatic and complex childhood. We've hunted for intermediate mass black holes, only to find their absence as puzzling as their presence would be, suggesting violent gravitational ejections from the very clusters that bred them. We've discovered planets surviving against all odds in gravitational maelstroms, and stars that cheat death, with blue stragglers stealing youth from their neighbors or being born again from stellar collisions. We've seen how these clusters are not permanent, but are slowly being unraveled by galactic tides, their stars forming ghostly streams that map the invisible dark matter of our galaxy. We've grappled with the profound distinction that while dwarf galaxies are dominated by dark matter, globular clusters are made of pure, visible stuff, a clue to two different pathways for building structures in the early universe. We've encountered hypervelocity stars catapulted into intergalactic space by gravitational slingshots, and we've used the incredible precision of millisecond pulsars as natural laboratories to test Einstein's theory of relativity. The discoveries stretch from the heart of our own galaxy to the farthest reaches of observation. We've seen how clusters can be factories for exotic X-ray binaries, and that some might even produce the colossal explosions known as gamma-ray bursts. We've found evidence that they played a crucial role in lighting up the universe during the epoch of reionization, and we've used their collective brightness as a standard candle to measure the vast distances to other galaxies. We've even detected the faint, mysterious glow of complex organic molecules within them, challenging our ideas about chemistry in pristine environments. And we've learned that some of the most famous clusters, like Omega Centauri, are likely not clusters at all, but the fossilized cores of galaxies consumed by our own in ancient mergers. Each of these 50 discoveries is a thread in a grand tapestry that depicts globular clusters as the universe's ultimate laboratories. They provide a unique environment where stellar densities are so high that processes which are rare everywhere else become commonplace. This allows us to study stellar evolution, gravitational dynamics, and high-energy physics in conditions we could never replicate on Earth. They are time capsules preserving a record of the early universe, and they are dynamic engines actively shaping their own fate and the evolution of their host galaxies. They challenge our models, force us to reconsider our assumptions, and consistently reveal that the cosmos is far more inventive and surprising than we ever imagined. The story is far from over. With new telescopes like the James Webb Space Telescope and the upcoming extremely large telescopes, we are on the verge of peering even deeper into these stellar cities. We will resolve their individual stars in galaxies millions of light-years away, obtain exquisitely detailed chemical fingerprints, and perhaps finally capture definitive proof of the elusive intermediate mass black hole. The next decade promises to unlock even more of their secrets, so the next time you look up at the night sky and spot that faint, fuzzy patch of light, remember, you are not just seeing a smudge. You are looking at a hive of cosmic activity, a place where the laws of nature are stress-tested, and where the next great discovery in astronomy is likely waiting to be found. We would love to hear from you which of these 50 mysteries captured your imagination the most. Do you have a favorite globular cluster? Share your thoughts and questions.